Good. You're right here. Right. For our last session of the morning, we have Mika Boynan presenting joint work with Paolo Ferrone on categorical algebra of conditional probability. You may start.
Yeah, thank you for the introduction. So as said, we talked is about categorical algebra of conditional probability, and it's based on my master's thesis, which Paolo here supervised. And so kind of the story here is focused on statistical experiments. And the point is that every statistical experiment produces a canonical decomposition of a state. And we can study sort of the informativeness and how they relate to each other through algebraic properties. However, the current theory depends on what Lenin talked about, Bayesian inverses, which, as she also mentioned, may not always exist. And so our contribution to this is sort of to break this dependency and do a purely algebraic.
Sorry, you're not sharing. That's okay. Continue.
Definition of hypernormalization. So, okay. More specifically, the key contributions we made to show that the theorem of that is Beck-Chevrolet, that there is a universal property of hypernormalization, which we are able to make because the Beck-Chevrolet model means that the partial evaluation relation is transitive, which we'll get into later. And then through this, we are able to give a alternative definition without Bayesian inverses. And sort of the point is, the work here is more synthetic than what previously has been done, which is sort of more based on measured theoretical properties. Now, luckily, Elena did a wonderful job of introducing Markov categories, so I was talk about the things she didn't do. Yeah, Markov category, it's a symmetrical category with a copy operation, discard, and such that they form a commutative comonoid. And also, the thing that makes it a Markov category is that monoidal unit is terminal. It's one of several equivalent definitions. Example, which is important for our work, is Borel-Stock, which is where objects are measurable spaces, or technically standard Borel spaces, which is Borel spaces with have certain nice properties. And morphisms are Markov kernels, and composition is via the Kaplan-Kolmogorov equations. And Borel-Stock is then the full subcategory of this with all these nice properties. And yeah, deterministic morphisms doing the same thing twice. It doesn't depend on the input. You get the same output every time. And denote the full subcategory by see that. Conditional. This is sort of equation, and again, it sort of allows you to bend wires, making you have state to outputs x and y. It allows you to sort of bend the wire, making x an input or y an input, depending on what you want for the moment. And so we say that the Markov category has conditionals if every morphism admits a conditional with respect to one of the variables. It doesn't have to be unique, but it has to exist. And then one of the most important definitions is that of a representable Markov category, which is sort of generalizing the concept that there is a probability monad underlying the category. So we do this by saying that the object has a distribution object, which is sort of the objects of distributions over that object. So, for example, in the case of Borel-Stock, the objects are measurable spaces, and then the distributions objects are kind of just distributions over that measurable space. And importantly, we get a natural isomorphism between homosets, and this makes distribution of these objects assembled together into a monad, which gives us a junction between C dat and C, as shown here. But now to the main story of this talk, which is statistical experiments and their relation between the compositions. So first of all, what is a statistical experiment? Well, you start with some probability space, theta comma p, where in this case p is just a state. And then a statistical experiment is just a morphism out of that state in some sense. So in this case, you have theta being the real line, and then p is a Gaussian on that, and f is the map from the real line to the 3-point set 1, 2, and 3, and then p is just push forward. So it's really just you have some sort of unobservable state, but you have some belief about that, and then you have an experiment to do, kind of sort of measure the temperature or see which day it is or something like that, which is sort of more coarse-grained than the original state. But the important part here is that a statistical experiment sort of partitions the original probability space into regions. And so this leads us on to standard measures or hypernormalization, as we call it, which is this thing. It's more helpful to sort of look at a concrete example. So you start with this original distribution, then you can sort of condition on whether the output is 1, 2, or 3. Depending on that, you get these three distribution values put up together in a sort of canonical way. And importantly, the weights they have to sum to 1 because it's a probability distribution of probability distributions. And the thing is, we can compare statistical experiments either through this sort of canonical decomposition or through a more probabilistic way. But we would like to do it in the algebraic setting, but let us first sort of understand the more traditional probabilistic ones, which is sort of really simple. If you have two statistical experiments, f and g, from theta to x and from theta to y, then we say that f is more informative than g if there exists a map h from x to y such that when you compose f with h, you get back g. So imagine, for example, you're measuring the temperature outside. And if you know the temperature in Celsius, that's more informative than just saying, it's hot or it's cold outside. Knowing if it's -20, negative or +20, there's a lot more information about the situation than just saying, it's hot, it's cold. Now, conversely, we have an algebraic notion, which is that of partial evaluations, which is a bit more technical, but sort of the intuition here is that compares how spread out a probability distribution is. So in this concrete example, you have sort of 3 Gaussians, and on this side you have 1, and these two merge. So you sort of take these two and you combine them together, then this you have lost some information here. There's more information in when you start with, so you sort of always go from there to there, but it's not equally as easy to go from there to there, right? So that's kind of the point about the partial evaluation order. And the important theorem here is that when if seen as an almost Schroeder compatible representative market category, and f and g are statistical experiments, and if they are related in sort of the informativeness, the usual Blackwell order, we say there's a map between the two. And this also means that their standard measures or hypernormalizations are related, which is a more algebraic way of looking at things. You don't really have to go into the probability theoretical notions of it. However, or to make this more concrete, I guess, f and g. F partitions into 3 regions, g into 2, and so we can sort of merge these 2 regions to get g. So that's sort of how the stochastic dominance order gives you the Blackwell order. It's maybe a bit hard to see, but that's sort of the intuition behind it. However, the problem is that the usual notion of stochastic dominance or standard measures depends on Bayesian inverses, which, as we said earlier, might not always exist. So we would like to sort of break free from this and have a purely algebraic understanding of what it means for statistical experiments to be related. So first of all, what is a Bayesian inverse? Well, it's an absolute result, which is the thing Elena talked about, which basically lets you update your belief after observing some outcome. So we have again this B and F, and then you can observe outcome one, you can update your belief about the private or the private distribution and get something new. And then you can normalize it to get a posterior distribution. But in, for example, the case where the prior would have been 0, there would be no kind of canonical way to update it. So that's also where hypernormalizations comes into the picture, because you don't have to worry about that all the time. Again, so yeah, the Bayesian inverse is critically in the definition of standard measures, which we would really kind of like to get away from. So our goal is sort of to get a more purely algebraic understanding of what the stochastic dominance order and how algebraic relationship between physical experiments relates. So how we do this? Yeah. And we would also like to kind of keep the connection to probability theory. So the new definition should not be something that doesn't specialize to the old understanding in the special case where we have conditionals. So this is really important. So the way you do that is by giving a canonical sort of building block, which is the Beck-Chevrolet condition, which means that when we have conditionals, we show that monad is Beck-Chevrolet, which means that the stochastic dominance order is transitive, which crucially means that we can sort of give a universal property in the categorical sense of which doesn't depend on Bayesian inverses. And then we show that in the case where we have conditionals, this is the exact same thing as what you would get with Bayesian inverses or the usual notion of standard measures. And so Beck-Chevrolet condition requires us to understand pullback, which is just a pullback that you don't require uniqueness, you just require that there exists some map. And you say that it is Beck-Chevrolet if the monad preserves three pullbacks and if the multiplication is multiplication, which means that every naturality square of the multiplication is a pullback. And yeah, so the point is for Beck-Chevrolet monad, the partial evaluation relation is transitive. And so this gives us a canonical way to understand or give a meaning to a universal property, as it would have to be a category for this to make sense.
Sorry.
Yeah.
You go back to one is the partial evaluation.
The partial evaluation.
Yeah.
That's this thing here. This thing here. So yeah. So if so the kappa such that this thing commutes, then pi is necessary to pi. Yeah. So
you use the component.
yeah, and this sort of captures this thing here.
So I could also imagine some was.
That's yeah, that's this thing. It's not entirely the multiplication, it's almost the multiplication, because multiplication would have to go from ppx to px, so the multiplication is actually p sum. But it's almost. Yeah.
That's really awesome. Like one.
Yeah.
You can go to I floating
And how do I get? Yeah. So
Why is this called back channeling? Because the condition gave doesn't look like the back channeling condition as I would expect.
yeah, I'm not entirely sure about that. I only know it as this thing. That's how I read it in the papers we referenced. That's how it's known. I don't know the story about why it is called Vecchia in just this case. Yeah. Like any other questions? No. Yeah. So the point is that Vecchia conditions ensures that the stochastic dominant order is well behaved, which means that a universal property would make sense. Yeah. And so in this new approach, we go from physical experiment, establishing the algebraic properties, then giving the universal characterization, and then using this new universal characterization to compare experiments, as opposed to the old one where you have to go through where you have to use Bayesian inverses, which may depend on some measure theoretical subtleties, which could be hard to deal with in some cases. And so the way you do this is, first of all, by showing that when the monad or the probability monad is Vecchia, then the hypernormalization or the standard measure of a statistical experiment satisfies this universal property, which is that for any other state which goes to p theta, such that it is a decomposition of p and it is compatible with the partition of f, then there's a partial evaluation from pi to the standard measure, which means that the standard measure is maximal among those states which satisfy these conditions. So it's the sort of the most refined decomposition of P that respects the partition structure of F. And every other sort of state can be coarse-grained, or decomposition can be coarse-grained into obtaining the standard measure. And this again then allows us to come up with this new definition, which is just saying that it is maximal amongst stochastic dominance order among those states satisfying these properties, which crucially does not force us to use the Bayesian inverses or the existence of conditionals. This is purely algebraic. You don't need to sort of depend on any measure theoretical subtleties in underlying market category. So it's a more sort of synthetic way to talk about and comparing experiments. Yeah, so this sort of highlights this. We only use algebraic properties and universal characterization. There's no need to go through the traditional way of using Bayesian inverses. But together you have to establish that the monad, in the case where we have conditionals, is Vecchia sort of show that this corresponds then to, or like the case without the purely algebraic case specializes to the probabilistic case in the case where we have conditionals. And so these are sort of the technical results we establish. In the case where C is an almost surely compatible representable market category with a monad, and if C has conditionals, the possible multiplication is weakly partition. There's also, but actually, you don't need a full BC condition for on the monad for the stochastic dominance order to be transitive. You just actually need that multiplication is weakly partition. And as a consequence of this, you also get that the 3D monad on standard Borel spaces has a weakly Cartesian multiplication. And the proof idea is sort of to do the obvious thing. It takes a little bit of thought, but you end up with sort of the only map which makes sense if you look at it hard enough. Yes. And crucially, you have to use the Bayesian inverse then. And for the case of preserving weak pullbacks, you also need something called the equalizer principle, which is just that equalizer in the deterministic subcategory exists, and that things factor nicely through the equalizer when you have morphism with a p almost surely equal. And how you prove this then is, the idea is that you first show that P turns fullbacks into weak fullbacks, and then that for a fullback in C dash and compatible morphisms P and Q form their conditional product, and then you show that this factors through the fullback. That's sort of the high level overview. And having done that, you end up with the fact that the monad is Beck-Chevalier, and also that sort of corollary of this is that the tree monad on standard Borel spaces is Beck-Chevalier. And this also means that the stochastic dominance order for the case of Beck-Chevalier monads is transitive, which means that the universal property characterization of hypernormalizations makes sense. It's categorical characterizations and not just a statement. So yeah, this is sort of, well, again, if you start with the Beck-Chevalier property, this enables a universal property of hypernormalizations, and then this sort of justifies the division-free definition, which is where we are able to break the dependence on Bayesian inverses. So, conclusion. The main results in our work is shown that the GV monad is Beck-Chevalier, that there's a universal property of hypernormalization, and we've also been able to give this new alternative definition. But it's sort of not entirely equivalency, because we've gone from the probabilistic notion to the algebraic part, but we haven't shown that this is sort of independent of online probability situation, because we don't know if in the Snow conditionals and the monad is Beck-Chevalier, if the Blackwell-Sherman-Stein theorem still holds, which is the one where we have, if the hypernormalization of F is greater than or equal to the hypernormalization of G, then is it the case that F is less than or equal to G in the Blackwell order, so that there exists a map between the two. It does in the case where there's conditionals, but we don't know if it does with no conditionals. And also, we don't really know if when there does exist hypernormalizations, does this mean that the stochastic dominance order is transitive? If the stochastic dominance order is transitive, then it makes sense to have the existence of hypernormalization, but we don't know the other way. So these are sort of the immediate questions. And then it could also be interesting to look at connections to, for example, vibrations and descent theory, and connect the sort of formalize the concept of applications induced by function to categorical descent, and perhaps develop applications in causal inference or similar areas. But sort of the big picture here is you have seen that, for example, the Finetti theorem can be studied through categorical means in marked categories, and now these were conditionals. So what else can we study through the lens of algebra and just this? And so that is what I will leave you with. Thank you.
Any further question?
Yeah.
Yes. Have you tried using the Radon model?
The
Radon.
Radon model.
no, I not looked at that. I'm not sure if that will if it will work that, but there's for sure that's could be something to look into.
I have a question. This algebraic perspective of statistical experiments, have you thought what are the practical implications? Like, does this lead to some alternative or new algorithm concerning these statistical experiments?
Well, it would allow you to determine when or compare statistical experiments in a purely algebraic way without having to use Bayesian inverses in your computer. And it would make sense even in cases where you don't necessarily have conditionals. So in marker categories which maybe topological spaces or something like this, you could sort of start to make sense of this and perhaps use that to improbabilistic program using like that. But yeah,
Is there some case study in Bayesian statistics that you try to approach this way?
yeah.
Perhaps doing something that wasn't done before because of this accrued generality?
Not yet, but that's for sure something to look into.
Okay. If there is no other question, thanks again to our speaker. We now take a break for lunch. I will resume, Matt.
One.
1:30.
Okay, yeah.
Okay, this is the first afternoon session today, and it is just a content session. And our first speaker will be Razin Shaikh, and he'll tell us about the popped up ZS calculus. Thank you.
Thanks, Amar. This is a joint work with Lee Agay and Stefano Gogioso. So here's the plan. So first I'll explain just the background about ZX, and how you use it for quantum computing, and talk about what this continuous variable quantum computation is. So in summary, we go from finite dimensional case to the infinite dimensions, and then I introduce the calculus, show that it's complete for Gaussians, and apply it to two examples, two things. Okay. So it is qubit quantum computing. So it's a symmetric monadal category, finite dimensional subspaces, where you have states that are vectors in 2 to the n dimensional complex Hilbert space. So it's 2 to the n because there are n qubits, and operations are linear maps. More specifically, in the circuit model, they are usually unitary maps, but there are more general cases where they don't have to be. Sequential composition is matrix multiplication, and parallel composition is a tensor product. Now, to reason about qubit quantum computation, instead of just working directly with the Hilbert spaces, we can have a nice graphical language, which is this qubit ZX calculus, which has two kinds of generators. The Z spider, which is the green one on top, and the X spider, which is on the bottom. And using these two spiders, we can reason about qubit quantum computing. And intuitively, what these spiders do is the Z spider is matches all the computational basis states. So 0 and 1 are the computational bases. It's right here, and the X spider matches all the Fourier bases, so conjugate bases. And this language is universal for qubits, which means you can represent any linear map of qubits with ZX calculus. And it was also proved to be complete. So just using these rules, you can prove any equality of qubit quantum computing. And since the completeness result, this graphical language has been applied to many applications, and there's a lot of ongoing work, and it's found to be very useful in quantum computing. And recently, there was this paper where we showed that the completeness of ZX can also be extended to finite dimensional Hilbert spaces. So not just linear maps between qubits, but any like linear maps, any finite dimensional linear map. So this kind of says that, okay, ZX is good for doing everything in finite dimensional Hilbert spaces. But what if we want to go further? And that's kind of what this talk is about. So I'm going to, in this talk, generalize ZX calculus to the infinite dimensional setting. In particular, apply it to continuous variable quantum computation. And why do I want to do that? Well, continuous variable quantum computing allows for simulating bosonic systems that appear naturally in nature and quantum field theories in a native way. Instead of like discretizing this continuous degree of freedom and trying to fit it in qubits, you can have more natural simulation. But I think more importantly, continuous variable quantum computers are proposed for quantum error correction, because you have a quantum computer which has continuous degree of freedom, and if you want to use, if you use the entire Hilbert space to store information redundantly, you can encode qubits in this bosonic Hilbert space and use the redundancy for performing very efficient quantum error correction. Moreover, there are already hardware proposals, implementations on many platforms, including photonics, superconducting, and trapped ions. So what is this? What is a continuous variable quantum computing? Well, we know that qubit is a single qubit. The state space is C2, and an arbitrary state is a superposition of 0 and 1. If you generalize this to qubits, we have D basis states, and a single qubit state would be a superposition of D computational basis states. Now, Q mode, which is the unit of information in continuous variable setting, the Hilbert space there is L2 of R, and we can represent arbitrary state in two ways. One, using the continuous degree of freedom. So you have ket X, where X is a real number. So this is like an arbitrary state. But also actually in the same Hilbert space, you can have the Fock states. So they go from 0 to infinity. These are the finite energy states. Oh, sorry, these are the energy states which are discrete. And we want to be able to reason with this sort of stuff. So in continuous variable setting, there are three natural orthonormal bases. And the reason we are looking at these is because in ZX calculus, if you look at the qubit case, you have two spiders, Z and Dx. They correspond to orthonormal bases. And we would want to do something similar in the continuous variable setting, where we have spiders corresponding to orthonormal bases. And the three bases that we care about usually are the position bases, the momentum bases. But these are the continuous ones, and they are conjugate to each other, so they relate by Fourier transform. But then we also have the Fock bases, which is a natural number basis. And they relate like this. To go from position to momentum, you can do Fourier transform. But to go from position and Fock, you can have this Hermite transform. And yeah, this is how the three bases relate. And so people know what Fourier transform is, but the example of Hermite transform is, here's how you can define the ket n Fock state using the position basis. So you have this psi n, which is the nth Hermite function. And these are like family of orthogonal polynomials. They kind of look like this. Not super important, except that you use their properties sometimes. Here. Sorry, what do you mean? So psi n is the n Hermite function. This is psi 0, psi 1. So okay, so with this, I can introduce the graphical language. So the generators of the ZX Celsius in continuous variables are, first of all, the Z spider. And this corresponds to the position basis. So you can see that just like the qubit base, this is matching the position basis states. And we will label the spider with some function f. We specify the coefficient of this diagonal map. So f of x is the coefficient of when you match the basis state to be ket x. For the Fock spider, we have it's the same thing, but now it matches the Fock states and it's discrete. And we have label which specifies the coefficient of the nth basis state. And as a generator, we'll also allow global scalars because it's easy to work with. So notice that we haven't defined X spider here as a generator because it's a derivable generator, because we can take this Z spider and put this minus I to the n Fock spider, which corresponds to the Fourier transform, and obtain the X spider. So the X spider, which matches the momentum basis state, is a derived generator here. Now, apart from spiders, it's also useful to have a little bit more syntactic sugar. Oh, so first of all, yeah, if the label of, if this is a constant function 1, then we will skip the label. Now, using these spiders, we can also represent the basis state themselves. So we can have ket x, ket p, and ket n represented like this. And more syntactic sugar is this thing called multiplier, which is defined like this, but it's not important. What it does is it sends ket x to get m times x, where m is the label. So it like multiplies the basis state. We can also define this W node. So in the qubit case, there is ZX calculus, there is ZW calculus, and this W node is a generalization of the W from qubits to the infinite dimensional setting. Semantically, what it does is if I input the Fock basis state as the input, like N1 to Nk, this W node adds all of them up. So it adds the Fock basis state into the one output wire. And this coefficient is like the binomial coefficient to make to get nicer rules. Now, so these are the so these are the generators and the derived generators. And with that, we can specify the rules. So the first rule is the fusion rule. You know, spiders fuse. The W node is a comonoid, so that also fuses. Then we have the copy rule. It says the spiders copy their respective basis states. And we have 3 kinds of bialgebra. So Z and X bialgebra is the is stuff you already know from ZX calculus. And there's a bialgebra between the Fox spider and the W node. And that's kind of the bialgebra that you get from generalizing ZW calculus. And there's also a bialgebra between the W and itself. The Fourier rule says if you have a state in the Z basis, so in the green color, you can write it in the red one by taking a Fourier transform. The second one is similar, where you can do the Hermit transform. And there are a couple of rules for multipliers. And yeah, then there are these last three rules, which are maybe slightly more complicated. The first is just Euler decomposition of rotations. This rule is like two equivalent ways of representing the beam splitter. And there's this fun rule, which is the triforce. Now, using these generators, we can define some of the operators and gates that we commonly see in the continuous variable setting. So we have the creation and annihilation operators. What they do is the creation operator creates a new particle that sends get n to get n plus 1. And that can be represented like this, where you have a W node and you just input get 1 as one of the inputs. The annihilation operator is the dagger of that. And we have the quadrature operator and number operator, which gives you the position or momentum of the input. So it's a very nice diagrams for these operators. But for doing computation, we need gates. And these are the single mode Gaussian gates. So Gaussian is like the Clifford fragment of the CV. So if you know, in the qubit case, we have Clifford plus T kind of thing, where Clifford is the classically simulable fragment, and you have something non-Clifford, which gives you universal quantum computation. It's similar to that. So these Gaussian gates are, if you just have Gaussian gates, that's easily simulable. So you have three Gaussian gates that are commonly used, which can be represented very nicely. And then there is the Gaussian entangling gate. So you have the controlled X, which is like the C0 gate, or the controlled phase gate. And here's the beam splitter, which is very natural to implement with optical setups. But to make universal quantum computation possible, you need non-Gaussian gates. And here are three options that we can choose, all of which have a very nice representation in the calculus. Okay, so these are the
Sorry, can I just
Yeah.
ask you on the slide? So there are three choices. Are you saying that all these three give you universality, or are you saying that they give you different extensions? And,
it gives you approximate universality. So you can approximate any
so each one of them gives you approximate universality?
Yeah.
Okay, thank you.
any non-Gaussian gives you approximate universality. So now I want to show that the calculus is complete for the Gaussian fragment. So the part that I said is easy to simulate. And as I already mentioned, the universal continuous variable gate set includes all the Gaussian gates and at least one non-Gaussian. And I want to show that the calculus already is complete for the first part. And here's how we can define the Gaussian fragment. So we will restrict to Z and X spiders, which have e to the I ax plus bx squared. So you only have linear or quadratic in the exponent. And we also allow delta 0, which is the vacuum state. So any diagrams that we can make with these spiders is a Gaussian diagram. So it's part of the Gaussian fragment of the ZX calculus. And for this fragment, we have the rule set that I presented before is complete. So that's what this says. Now, to prove completeness, we will translate the completeness of a different calculus, which is graphical symplectic algebra. which was introduced last year. And it has semantics in relations. But it can represent all the Gaussian maps in this calculus. And because it's Gaussian easily simulable, it can give relational semantics and prove completeness very easily. So what we do is and these are the complete rule set for it. So what we do is we show that there's an invertible translation between our calculus and graphical symplectic algebra. And all of the rules of the calculus can be derived from the rules of our calculus. We also need to show that the semantics of like relations and our semantics is compatible. And yeah, then we have completeness for the Gaussian fragment. All right, so now let's try to apply this graphical language to do something useful in quantum computing. So one such thing is doing error correction. So there's this proposal by Korstin, Kitaev, Preskill from 20 years ago of how you can encode qubits in these in this infinite dimensional setting, and which are called the GKP qubits or GKP code. And there are several companies that are actually like planning to use this as their as their main qubits. Like Xanadu this is their main proposal. So you can represent 0 and 1 as a superposition of like basis states that are separated by 2 squared root of 5, and so that's 0, and the ket 1 is like shifted a bit. So superposition of all of these states is ket 0, and if you shift it a bit, you get ket 1. But now, since we can label any function on our spiders, we can simply like label the spiders using the appropriate functions to get these basis states. But this is an ideal GKP qubit. In the lab, what you can actually implement is stuff with where there's finite amount of students. It's like normalized in some way, and we can show that we can get a very nice graphical description of this by showing that the approximate GKP qubits are same as the ideal ones, but then you add this Gaussian blur in Z and the X spaces. And it becomes very very visual when you write it in diagrams, that this is what's happening, which is not so clear in the actual expression. Now we can define the encoder. So usually error correcting code is defined by a map like an isometry, which shows how qubits are encoded in like a higher dimensional space. And you can define this encoder by observing that if I take ket 0 and if I shift it by square root of pi, I get ket 1. So I can use that idea to get this diagram, where if I put ket 0, I get ket 0 logical qubit. And if I put ket 1, it shifts 0 by square root of pi and gives me ket 1. So that's the intuition here. And now if I define this this notation, which is the mixed dimensional Z spider, so it's simply an embedding which encodes the 0 qubit state into 0 position eigenstate and 1 qubit state to 1 position eigenstate. Then this diagram is the encoder circuit or encoder linear map for the GKP code, which we can verify here. And once we have this encoder, we can start obtaining logical operation by pushing through the encoder. So I want to know what this operation, which I want to do in the qubit land, how do I actually physically implement it on my continuous variable system? So I can apply the rules to take this thing, push it all the way to the right to get something else. And now this is the operation I need to do on the continuous variable system, such that the effect is doing that gate on qubit. So having an encoder gives you like a rewritable way of like obtaining logical operators. And yeah, so far I only showed the encoder for like encoding one qubit into one Q mode, but you can get a more general form where you can sort of show that any GKP encoder is you encode one qubit into one Q mode, and then the rest is just a Gaussian unitary with some ancillas. So yeah, this gives us a very powerful framework for deriving logical operators. And this framework is also used in qubits to reason about like properties of the code and show when two codes are equivalent or how you can go from one code to the other. So we might be able to like quote some of those ideas and result in the continuous variable case. And we can also use this to talk about how you can detect errors and correct for them. So this is syndrome measurement circuit. This is just a GKP state. And you can show that if there is an error that happens on a state, we can show that measurement output gives us the error, which we can then simply correct by shifting in the opposite direction. Okay, so now I'll talk about the second application of Gaussian boson sampling. The Gaussian boson sampling is not a universal model of computation, but it's proved that this is equivalent to like sampling from a Sharpie-Hart problem. So there have been several papers and experimental demonstrations of quantum advantage by using Gaussian boson sampling. And what we do now is we can show that Gaussian boson sampling is hard diagrammatically. And the reason why it's hard is because the amplitude is proportional to the Hafnian, and this Hafnian function is Sharpie-Hart. And to do this, we note that the way Hafnian can be understood is it's like perfect matchings of a graph. And because that's the case, we can actually represent perfect matchings of graph in ZX. So if you have any graph which can be connected by the W nodes, post-selected on Ket1, then that diagram, that scalar, is same as the Hafnian, which is number of perfect matchings. And it also works when you have weighted perfect matchings. So using this intuition, we can prove that given any adjacency matrix of a graph, we can a diagram of this form where the connectivity is given by the adjacency matrix of the graph is the Hafnian. The actual proof is by induction. But then we can take the Gaussian boson sampling circuit, here's an example, and try to get to this form. And if we can do that, then we get the Sharpie hardness of the Gaussian boson sampling problem. And what we do is in the circuit, this part is called the interferometer. And it's already known that this interferometer can be represented by this bi-adjacency matrix of W's, and so some unitary in the middle, some matrix in the middle. It looks like this. And then we can compose with the initial part, which is the Gaussian boson sampling, which shows the entire Gaussian boson sampling circuit. And then we can rewrite this into this form. So we get a normal form for Gaussian boson sampling circuit. And now to sample the amplitude of measurement, we can simply plug in the states that we want to sample, and that corresponds to the Hafnian. Okay, so this shows that Gaussian boson sampling is a Sharpie-Hart problem. And we can have a diagrammatic proof of that. Right, to conclude, we have generalized ZX calculus to infinite dimensions, and we have continuous as well as discrete generators, and it's complete for the Gaussian fragment. And we also showed a graphical analysis of GKP, error correction, and Gaussian boson sampling. For future work, it would be great to generalize the results and tools that have been developed for qubit ZX to the continuous variable settings. So specifically, generalized algorithms for compiling, circuit optimization, doing classical simulation, and also measurement-based quantum computation. Moreover, it'd be interesting to prove Gaussian completeness of a different fragment, where you just have Fox spider and the W node. And finally, it'd be good to prove completeness for the approximately universal fragment, although I expect that to be pretty difficult. And finally, generalize the error correction toolkit from qubits to CD, specifically doing things like Pauli webs and flocatification, which can reduce the measurement weight, and do more analysis of multimode GKP codes and concatenated GKP code, and go to other bosonic codes like cat codes and binomial codes. Yeah, thank you.
So you're obviously having your scalars are functions. And so you're doing computations in some continuous function algebra. How much of that do you need to get an approximately universal fragment? And what can you say about the computational aspect of that?
I don't understand functional.
Scalars or actually functions.
Mhm.
Interpretation.
Yeah.
So, so when you're doing like the fusion rule and so on, you're multiplying functions or so, doing some function algebra, continuous functions. I'm just asking, how much do you need to get an approximately universal fragment? And what can you say about the computational aspects of that?
So the rules where functions are involved are like whether you have like, but there is the pointwise multiplication of functions. That's the first one, and then there are these rules where you do Fourier transform or Hermite transform of functions. So, I mean, I think most generally, like if you could do like one-dimensional integrals, that should be sufficient. We can, yeah. So the only operations that really happen are function multiplication pointwise, Fourier transform, and Hermite transform. So that's basically what we need. For getting completeness, I'm not sure. I expect there to be some non-trivial rules which relate specifically to the non-Gaussian generator. But yeah, I don't know what would be necessary there to prove completeness.
Other questions?
There's stuff here.
Yeah, are there any questions?
No, it was just some mic issues.
Okay, I'm going to just ask one more question. So you said that you expect that the proof of completeness for the approximate universal fragment is going to be significantly harder. So I guess that means that there is some fundamental difference from the finite dimensional case, because there. So what would you say is the main difference by which the techniques used in the finite dimensional case will not work? Yeah.
I don't know what normal form could be. So if you consider the universal fragment, that's like for finite dimensional setting, you can just have the actual semantics of the diagram. So like the entire matrix in your diagram as a normal form. But of course you can't do that here because it's infinite dimensional. So doing completeness for the entire universal fragment seems extremely difficult, and maybe it's easier for the approximately universal case, but I can't see what normal form we could use for proving completeness. So I guess that would be the difficulty.
Yeah. Okay. Then there are no more questions. Let's thank the speaker again.
This one right here. session.
You're just.
Yeah, sure.
Okay, second speaker is Thea Lee from INRIA Sacre. And she will tell us about the category of finite dimensional operator spaces. Thank you.
Thanks. Just to note, this was part of my like M2 internship project, and it was supervised by my now one of my now PhD supervisors, Vladimir. I'm gonna zoom out a little bit and like give some motivation behind like why you should care about operator spaces, because like while you might think that the like mathematical structure is quite interesting, which I do, but why should you care? So we have two views on the quantum operations. There's like the Schrödinger view and the Heisenberg view. And for me, I like category theory. So for me, these are organized into two categories. In the Schrödinger view, we have objects that are finite dimensional Hilbert spaces. And then for the morphisms, we have completely positive trace preserving maps between the trace class operators on these Hilbert spaces. And then in the Heisenberg view, we have same objects, but the morphisms are normal, completely positive unital maps between the bounded operators on these Hilbert spaces. And the way these two views relate to each other is through something called the Heisenberg-Schrödinger duality. So if we're given two Hilbert spaces, there's an isomorphism between like the CPTP maps on the trace class operators in one direction, and then the NCP maps in the other direction. And this, of course, gives us an equivalence of categories from like S to H up. But to describe this, it's kind of annoying to have two different categories. We would like to organize all of the data into like one category. And then we can note here that we're talking about completely positive maps. So being completely positive is not just a property of the linear map from on the trace class operators or on the bounded operators. It describes some property that the like induced maps on the like matrix spaces has. And the theory in which we usually talk about this is called operator space theory. And it's seen as like the non-commutative or quantized version of like Banach space theory. And we'll see that some of the properties of like the category of finite dimensional operator spaces that kind of parallels the Banach space equivalent. And it's also like, it's been studied quite extensively from like a functional analysis point of view. So there's like a lot of already interesting results. There's a lot of interesting constructions that just like haven't been done through like a categorical point of view before, or not as much at least. So there's a lot of like interesting tensor products. And one of the interesting ones is actually like a non-commutative and like self-dual when the spaces in question are like finite dimensional. And this property, I think, is quite rare among the like kind of natural mathematical tensor products. And indeed, like the bounded operators and the trace class operators are operator spaces. And the bounded operators on a Hilbert space is the like operator space dual of the trace class operator. And then we also have like tensor products that work nicely with these two constructions. So I think this like gives a good argument for why we should consider like operator spaces as like a basis for talking about the Heisenberg-Schrödinger duality. So concretely, an operator space is a closed linear subspace of the space of bounded operators for some Hilbert space. And this is seen as like a norm linear space. So the inclusion in like gives a norm on the subspace. And now we can note that this inclusion induces an inclusion of all the like matrix spaces over our subspace into the matrix space over like the bounded operators. And the matrix space of the bounded operators is again like a space of bounded operators on a different Hilbert space. So this inclusion also determines a norm from like the matrix space. And all of these, like, each of the norms of the like sub or like the sequence like matrix space are all like supremum norms. So they're quite like nice norms. They satisfy some nice coherence conditions. And one of the like main results in operator space theory is that there is a fully abstract definition of this. You don't need to like point out which like B of H that you embed into. So you can just give like a space and then like a sequence of norms on the matrix spaces. So some common examples include like the space of complex numbers. It has, is there a way to take away this?
You just have to click it.
Okay. Or I can do that. Sorry. No?
Just click it.
Okay, good, thanks. So the complex number, yeah, they're like operator space structure from the isomorphism between like C and the bounded operators on C. And then of course like B of H and P of H for both operator spaces. And then for each Hilbert space, there's another operator space structure on it given by like the isomorphism between H and the bounded operators on like from C to H. This is called the like column space on H. No, we're going to talk about a category, so of course we need morphisms. Yeah.
Wanted to clarify, in your vertical space, do we need like supergiant space?
No.
No. And you don't want use?
No, this is called an operator system, I think.
Yes.
What's different, like, but operator systems are operator spaces, like with extra data. So maps. We're interested in this like matrix structure, so the morphisms kind of need to reflect this. So if we're given a linear map, we can note that this linear map on between operator spaces, they induce like a linear map between the matrix spaces. It's just given by like entry-wise application. And now we can define a norm on maps between operator spaces. It's called a completely bounded norm. And it's given by the supremum of all of the norms of the amplifications, which are these like induced maps on the matrix spaces. So for something to be completely bounded, it's not sufficient that each of the like amplification are bounded. The bound of the amplification or like the sequence of bounds also need to have a bound. We call a map completely contracted if the completely bounded norm is less than or equal to 1. So the category that we're now going to talk about is called FDOS, and we have objects that are finite dimensional operator spaces. And then our morphisms are completely contracted maps. And for the remainder of the talk, we're going to like see that this gives us a model of multiplicative additive linear logic, the classical version. We'll mainly focus on like the multiplicative fragments, because that's the interesting part. And then we'll also proceed to verify that it's a kind of natural or like mathematically nice BB category. So for those who don't know, classical multiplicative linear logic, in here we have a syntax. In the syntax, we have like a dualizing operator, and then we have 2 binary connectives. There's the multiplicative conjunction, the tensor, and then there's the multiplicative disjunction, the par, and then like the linear implication is given in terms of the par. And these 2 connectives are assumed to be associative and commutative. And then they're each other's like De Morgan dual. They each have their own unit. And then we assume, since we're in classical logic, or like classical linear logic, we assume like double negation, so the double negation of a formula is the formula itself. The inference rules are given by like a sequence style in like a sequence, like against in sequence style. So we have an axiom and then like a tensor introduction and a part introduction. The categorical version, or like to model this categorically, we use like star autonomous categories in general, which are symmetric monoidal closed categories with like a dualizing object, which are denoted by balls or bottom. And we assume that the transpose of the evaluation map into bottom is an isomorphism. So this says basically what forces an object A to be isomorphic in a canonical way to its double dual. Quite straightforward. We interpret like the connectives by like the dual is just like the internal home into this dualizing object. The tensor is the monoidal product. The par is given in terms of like the dual and the internal home, and then like the unit of the tensor is the monoidal unit, and the unit of the par is like the dualizing object. And then the coherences and the inferences are isomorphisms and morphisms in the category. They're both like in a canonical way using this structure, but for later reference, we can express them as like natural isomorphisms and natural transformations. So you can see here that we need kind of constructions on operator spaces to build this structure on FDOS. And just as for any like normed space or like any vector space, we can define like a mapping space on operator spaces. And here it's given by the space of completely bounded maps between two operator spaces, with operator space norm given by the like completely bounded norm that I defined before. And if we instantiate this with like codomain, that is the complex numbers, we get a nice notion of like dual space. And then you know that this is functorial and it's like it has like a universal property with respect to something called jointly completely bounded maps, which is like the operator space version of like bilinear maps. And then when a space is finite dimensional, it is canonically isomorphic to its double dual space, like vector spaces. For the tensors, the ones that are interesting here is like the projective tensor and the injective tensor. And the projective tensor is like the object that characterizes jointly completely bounded maps. And this is like the maximal nice like matrix tensor that we can find. So since we're interested in completely bounded maps, it has like a mapping out property. And then for the injective tensor, the norm is induced by the inclusion of like the algebraic tensor into this completely bounded space. And in the finite dimensional case, these two spaces are isomorphic. So the injective tensor will indeed be this like completely bounded space. But in the infinite dimensional one, it's like it's not, so it's its own tensor product. And these two are, of course, also functorial with respect to CD maps and CP maps. They're both like symmetrics or commutative if you want, they're associative, and they both have units, that is the complex numbers. So we puzzle all these together and like modulos and like coherence diagrams. We can verify the FDOS equipped with like the projective tensor and the CD space is a monoidal closed category. And now for the like MLL structure, we have that it's star autonomous and like multiplicative conjunction is just given by the vector tensor. The par is given by the injective tensor, and then like this dualizing object is C, which is the same as like the monoidal unit. It's like the dual space of is, or like the CB space from C to C is again C. And the dual operator is just like the operator space dual. And indeed, we have this like that a space is isomorphic to its double dual. To add like the additives, we just need to verify that FDOS has products and co-products. And these are like with finite spaces given by the operator space version of like the L infinity and like the L1 direct sum. They look like this, but it won't be like important for the next part. So I just thought it would be interesting to mention. I also said that FDOS is a BV category, and BV categories are defined as like the category version of something called BV logic, which is an extension of like classical MLL. So the new thing here is that we have another binary connective called the SEC, and it's assumed to be associative, and also that it's like self-dual, so like the negation or the dual of the A sec B is like A dual sec B dual. And we assume that the unit is self-dual as well, but we don't require that the sec is commutative. So for the inference rules, they're given by like a deep inference style system. And this means that we can apply the rules however deep inside of like our context that we want. So for the rules, we can like introduce a unit anywhere in our context. When you have introduced a unit, which you can always do, you can always like use the axiom. You have linear distributivity, just as with ML. And then the new thing here is this like interchange rule between the tensor and the sec. And now I think that this is like a quite common opinion, but I think it looks like the deep inference suggests that like inference rules and coherences and like the categorical versions should be like natural morphisms or like natural maps or natural transformations. Yes, sorry.
The inference rule was sort of co-evaluation, right? The one from I to I A bar A star.
Mm-hmm.
So there is no evaluation. So from A to star. So
Oh, but you can always take the dual because we're in classical. So like you have the dual of all of the rules and you kind of have, yeah. So for the category version, I'm not gonna say that this is like models because I don't think anyone's proved like an internal language results. But the categorical version is called like BV categories with negation. And it's like a star autonomous category with an additional monoidal structure that is normal droidal to the original monoidal structure. And this means, the droidal means that we have like a natural morphism or like this natural morphism or natural transformation that you can see that it's just like the interchange rule. We assume that the normal means that the unit of this additional monoidal structure is isomorphic to your original one. And when this was introduced, it was proved that by the people who introduced this, that the self-duality of this like additional monoidal structure can be derived just from these premises. So it's not assumed as a premise. So what's missing in FDOS is that we need yet another tensor. And I mentioned that there was a self-dual tensor before, and it's called the Hager tensor product. And it's defined using something called the matrix inner product, which is just like, it's like matrix multiplication, but with multiplication replaced by a tensor. And now the Hager norm is defined as like the infimum of all the norms of all the like matrix inner product decompositions of an element. And now the Hager tensor product will be like the norm completion of like the algebraic tensor with respect to this matrix norm, or with respect to the Hager norm. In the finite dimensional case, the like underlying vector space will just be the algebraic tensor product, and then we just like slap the norm one. And this is quite a nice tensor product. It has like a universal property that says that if we have a linear map from a Hilbert tensor into like a space of bounded operators, this is completely bounded if and only if we can like factor it through two completely bounded maps through another Hilbert space. And some of the interesting properties here is that, well, it is self-dual in the finite dimensional case, and then it's like genuinely like non-commutative and non-symmetric. Because like if we're given a Hilbert space H, even in like the finite dimensional case, and this is the finite dimensional case, sorry. So if we're given a finite dimensional Hilbert space, we take like the column space of this, and we Hilbert tensor it with its dual space, we get like the bounded operators on H. Whereas if we do the opposite, we get the trace class operators. And these are, well, non-isomorphic because the norms are completely different. So the Hilbert tensor product is also vectorial, it's associative, and it also has like unit given by the complex numbers, no surprise. And all of this, from all of this, we can deduce that F DOS with this Hilbert tensor is a monoidal category. So F DOS is indeed like a BD category with negation because it's star autonomous. We can build the dual of the interchangeable using like leveraging functoriality of the Hilbert tensor with respect to like completely bounded maps, and then like using the self-duality and then just like take the dual of this, and since we have double negation, this is fine. And as we have the same unit as for the projected tensor, we have normality as well, so it checks all the boxes. Sorry. Okay, yeah. I just have 2 slides. So that concludes like the main like body of this talk. I just want to zoom out a little bit because I mentioned like the Heisenberg-Schrödinger duality. So now how we see this in FDOS is that we have 2 full embeddings of H and S into FDOS. And now using the 2, we can see that the lift, we have this dualizing functor given by the like operator space dual. And if we lift this equivalent of the categories with respect to these 2 embeddings, like recover the isomorphism of the categories between like S and H op. The annoying thing here is that this embedding is not full. So consequently, there are morphisms in FDOS that do not correspond to like nice content operations. So what we would like, jokes aside, so a part of my PhD project is to build like a category that is morally like a category of operator spaces where there are full and faithful embeddings of H and S. And then like we want to recover this duality of H and S and E. And then like this also should inherit like the ML structure from FDOS. And we want to like preserve the non-commutative structure as well. Maybe I won't talk about this because this is going to take a while and I didn't have that much time. So I'm just going to end there and just like a small sketch of what like we've been working on. So thank you for listening.
From a logical point of view, there's some degeneracy in the units, I was saying.
Is there
So in ordinary linear logic, I mean, that would correspond to having the monoidal unit being the same as the sort of unit for the car is like the Murray version of the mixed rule.
Yes.
Then when
Yes.
you relate it to proof nets, you drop the if I remember correctly, the connectedness condition.
Yeah.
And now you have also a triple, you have an additional thing that the unit of the
Yes.
sequential one is. So can you account for all of that proof theoretically?
I don't really know, because like, well, I don't really know too much about PV logic from theory point of view. But it is sort of, yeah, I don't know for this, the logical structure of atoms. I don't know, it's something that I need to think about, but I don't know.
Generally, I'm, based on my experience, the trace preserving and the completely positive side are also based on the fact that you have a unit, or you have an ideal units.
Yes.
So, like, for the first thought on this slide, this fullness. First of all, requiring you to get something like a unit, meaning given an approximate unit or something like that.
I mean, both like, so we want both like CPTV maps and NCPU maps inside this category and between objects that are morally like B of H and T of H. And one of them, like B of H is already like an operator's system, which has a unit. The other version is not an operator's system, but the maps there are like the operator space dual of like the thing with the like unit. I don't know if that really answers your question, but
You will maybe tackle that with an approximate unit, because I think that should be like. But just pointing out.
Sure.
Thank you for.
Thanks.
Thank you for the talk. I wanted to ask if you've sort of encountered like the Wheeler dual.
Sorry?
The Wheeler dual of an algebra.
No, I don't think so.
Because it seems like you have like the finite dimensional assumption, because when you like take the dual, it only has the required structure when it's finite dimensional. But like this kind of happens in the Wheeler dual as well, where if I have like an algebra of a field and I take the Wheeler dual, if I take the dual, it's not a co-algebra once it's finite dimensional. So in the Wheeler dual, you just say I take the largest co-algebra, like sub co-algebra of that dual. Like you're kind of just taking the biggest thing that fits your description. And I'm wondering if you can kind of apply the same technique here to get rid of the finite dimensional assumption.
Not sure that this still the problem with like infinite dimensions. It's like in the finite dimensional case, we really like leverage rank nullity theorem from like vector spaces. So I'm not sure what really happens if you like change the dual in some way.
Right.
So I don't know. But thanks for mentioning it.
Thank you.
Any more questions? Okay. Let's thank Freya again.
Going on. Good. Yeah.
Okay, so our last talk in this session will be given by Hamza Wassim from Continuum, and he will tell us about teaching quantum theory with a compositional lens. Thank you.
Thank you, Amar. So I'll be speaking about our recent study where we used qubit ZX calculus to teach quantum theory to high school students in the UK. So this study was actually conducted in the summer of 2023. We have just announced the analysis of, results from this study, and it's available on arXiv. So I'll walk you through the course, how it was set up, the logistics of the course, what was the material that was taught, the challenges we faced, and what we learned from this study. So this project is not by me alone. This is the whole team. I think there are more people involved as well. There were quite a few tutors who taught the course, and there were more people who were involved with the logistics as well. So normally when quantum teleportation is taught, it's usually like this, Hilbert spaces, linear maps, tensor products, and this is a picture of quantum teleportation lecture notes from a master's course. But physics can also be done with diagrams, and there is a good trend of doing it, going back to Richard Feynman and Roger Penrose. So in 2017, I believe this book was published called Picturing Quantum Processes, and it is basically the default quantum computation and processes course at Oxford. And this course has been taught for more than 10 years, I believe. I believe many people in this room have taken this course. So the good thing about this course is that it teaches quantum theory, with no physical prerequisites, but there are still mathematical prerequisites. So there was this belief that quantum theory could be taught with absolutely no mathematical prerequisites. And with this belief, a new book was published a few years ago called Quantum in Pictures. So this, the approach is to teach quantum theory, head on with ZX calculus with no mention of symmetric monoidal categories or any of the technical jargon that we are so much used to and that we love. The main protagonists of this book are, of course, spiders. And to just give you a flavor of what's in the book, I'll show you some material. So this is spider fusion for green spiders. This is, so we call it leg chopping in the book, but you all know this is complementarity. When green and red spiders interact, and if they share 2 legs, then you can chop the legs. And these are some examples. And just to give you an example of a C0 gate, what happens if we connect 2 C0 gates? You can simplify the diagram diagrammatically, and you can show that applying C0 gates twice means that you do nothing to the 2 qubits. Now we can take a slightly more complex example. There are 3 C0 gates, and applying the fusion and leg chopping rules, we can show that this circuit on the left-hand side simplifies to the one at the rightmost. Using just 2 rules, spider fusion and identity, we can actually teach quantum teleportation. I'm not going to go through this whole derivation, but if you compare this to the traditional quantum teleportation example that I showed you, you can pretty much see that there is some difference in the kind of complexity and presentation, of course. There's more in the book, and this book has been approved by kids. This is feedback from Dan Gika's son. So Alexander was 10 years old, and he said that this book is very clear, very well structured, easier to understand than science YouTube videos. So that's quite something. But people may say that this is a biased example because this is Dan Gika's son and not an ordinary kid. So we decided to actually test this hypothesis. We wanted to see whether quantum pictorialism can be learned by 16 to 18-year-old students. And in the jargon of education theory, we wanted to show whether quantum pictorialism lies within the zone of proximal development. So this yellow zone is basically all the tasks that learners can do without any help. This light blue zone is the zone of proximal development, ZPD. They are the tasks that learner can do with assistance, so maybe some tutor, some teacher. And the outside circle is basically the tasks that learner cannot do, even with assistance. The key performance indicator we took was performance on Oxford University postgrad level exam. And the course was set up pretty much like an Oxford University course. So 8 weeks of tutorials, 1 lecture every week. Then there was 1 tutorial. The lectures were pre-recorded. So this whole course was basically organized online. This is the flyer that we circulated on social media. Within 3 weeks of announcing it, we had more than 700 applications. We selected 76 candidates randomly, but we made sure that they had fluency in English. They could commit at least 2 to 3 hours per week. And we also made sure that there was gender balance. Out of the 76 candidates, 54 completed the course, which means that they attended most of the lectures and tutorials, and they also completed an exam at the end.
Maybe I should change those bullet points, because it reads like 0 fluency, 0 time, and 0.
Oh, sorry. Well, yeah, maybe that's another study for future. Thank you. Okay, so these were the concepts that were taught. And obviously, we didn't use this terminology. There is a kind of funny terminology that is in the book. So, yeah, so for example, let me try to give you some interesting example. States are states, of course. Gates are gates. Entanglement is entanglement. So probability was introduced with some kind of lottery. Unitary maps were basically double flip undoable maps, which may be a mouthful. So I mean, there's a discussion about whether we should use the original terminology or go to a simpler terminology, but that's another discussion. So the weekly lectures were recorded. They were put on YouTube. We are going to release all this material for the general public very soon. These lectures were taught by a number of people at Quantinuum and University of Oxford. There were quizzes as well and quiz solutions. I believe these solutions were recorded by Bob in his office. We also gave everyone certificates at the end. And so the thing about certificates, we made sure that everyone got a certificate regardless of the mark that they got on the exam, and the students knew it. So there was no pressure on the students to perform well on the exam. They just had to complete the exam. This is some information about the exams. The exams were basically taken from the quantum computer science and quantum processes and computation past papers. They were obviously, they were translated into the jargon for kids. And this exam was a take-home exam of 2 weeks. It was doubly blind marked by Oxford professors. And we also collected some data. So we collected demographics data, some qualitative data through attendance, tutor feedback, some pre and post-study assessments. And obviously, the most important part is the performance on the final test. So this methodology is explained in this paper, which was released last year. It was also presented at a IEEE conference, but you can find a free version on arXiv. And these are the exam outcomes. So 54 students completed the course, and more than 4 in 5 students passed. Almost half got a distinction. So this is based on Oxford rubric. Now here, what's important is this asterisk. So there was a very simple question, which was very much a definition question in the exam. And some students got it wrong. So we believe that these were the students who didn't pay attention to the course. And if they are getting a definition question wrong, they obviously weren't able to do the rest of the exam. So if we filter these cases out, then we get 82% pass rate, half distinctions. But if we don't remove if we don't filter out these people, then we get more than 35% distinctions, which is basically a score higher than 70 out of 100. And this was the number of distinctions are the distinction percentage is higher than the fail percentage. So I think it is reasonable to say that quantum pictorialism lies within the zone of proximal development. But again, this is the least interesting part as far as I'm concerned. the more interesting part is what we'll talk about now. So the participants came from a very diverse pool, both ethnically and educationally. You can clearly see there's a nice mix of state schools, grammar schools, private boarding, and a number of ethnicities. And I mean, since the study was just in the UK, so it is not surprising that the biggest ethnicity was white, but even then there's a good mix. Another interesting observation was that there was a poor correlation between the exam scores and thus the number of hours that the students spent studying. And there was also a poor correlation between the exam scores and their school grades in maths and physics. So this may indicate that quantum pictorialism is actually, useful even when the students don't have traditional competencies that are tested in school. We also asked the students if they had any previous exposure to quantum physics. Most of them didn't. 80% had limited to zero knowledge. And about 66% students didn't need more than 2 hours per week of study. So this was during the summer, and as many of people can relate, I'm sure, O-level students are doing a lot of stuff apart from, vacationing. So they had part-time jobs, internships. They were also preparing for their GCSE exams. So we also asked them whether this course motivated them to pursue STEM careers. 90% of them said it did. 70% agreed that the course strengthened their motivation and confidence in general. I know anecdotally that 3 or 4 students later got offers from Oxford undergrad. Majority of students said that the tutors' communication was either good or very good. Again, this was a mix of employees of Quantinuum, but also PhD students and postdocs at Oxford. And there was a highly significant correlation between the evaluation of tutors and the course leading the students to pursue STEM careers. So of course, teachers matter. So we also, we also tested the age thing. So this was a very small window of age, 16 to 18, and there was no significant trend. There was 16 and 17-year-olds performed slightly better than 18-year-olds, but this was not statistically significant. So in future, we are hoping to do a study with younger students, and we believe that below the age of 13, there might be a trend because younger students might need some more attention from the teacher. There were, of course, lots of challenges. The study was completely online for logistical reasons. Because Oxford University was also involved and these students were 16 to 18-year-olds, we had to get some ethics approval and paperwork done. It took years to get this kind of work done. And we were also not allowed to use, so we wanted to use some interactive kind of social media, so something like Discord, where the students could also interact, but we were not allowed to do that. And there was also not much interaction between the students, which I think is a disappointment, because in education, it's important that students interact. And most of these students were, again, remember that this study was done in 2023, towards the tail end of COVID. So these students were used to online schooling. And remember that these students were teenagers as well. So they were already shy, and then there was the effect of COVID. So these students were not participate. A lot of these students did not actively participate in the online live tutorials. Many of them would not even turn on their cameras, so it was hard for the tutors to gauge whether the students were getting something or not. And again, this study was limited to students in the UK because the ethics approval was only for UK students. So again, and this was a small size as well, 54 students completed. So in the future, we plan to do large scale studies. As of a few weeks ago, all this analysis available on archives, really long paper. Feel free to browse after the talk. This work also got a lot of media attention. This is some coverage in the media. In the US, there is a consortium of quantum technology companies in Colorado, and they also endorse this work to train the future workforce of quantum scientists and engineers. A lot of stuff is happening right now. We are planning to do a comparative study of the effectiveness of quantum pictorialism and the traditional Hilbert space bucket approach. And we want to compare how, which approach is more useful or more effective to teach certain ideas. And qualitatively, we know that the averages and the distinctions we got from our study are actually better than like Oxford University statistics, but we would want to do like a comparative trial. We are also planning to release all the course materials, which includes a free PDF of the book. There are some translations in the works as well. This is the Greek translation, which is already out. There is an ongoing trial in Greece where they have introduced this material in the national high school curriculum, and they are testing it with 200 students distributed in a number of institutions. There's also some teacher training for Denver public schools in the USA, and in the Denver public schools, they want to introduce this kind of material at even primary school level. So there is some conversation and discussion with Denver public schools. There's also a study in Sweden, and since this year is the International Year of Quantum, we have planned some workshops and courses in the USA, Dubai, Morocco, and Pakistan. For more details, you can visit the papers. There's also a blog by Bob Coca on Medium. Thank you very much. Yeah.
Oh, yes. What are the students struggling most with? The concept.
There are two answers. There's an answer that is restricted to the study, and there's an answer that is beyond the study. So the answer that is restricted to the study is, there are some calculations that students struggle with, because a lot of this course was about calculation, right? Because this study was not really testing their concepts. It was more about, here's an entangled state, and you do something, Alice applies a particular operation to her part of the state. What does Bob get? Or some kind of teleportation or communication protocol. Yeah, but outside the study, I think, again, this is not about this study. I'm speaking generally because I also teach this course at the university level, and so students sometimes struggle with concepts, because in this kind of teaching, sometimes it becomes so much about mathematics that physics takes a backseat.
This way.
No. I'm talking about quantum in general. Yeah. Thank you. Any other questions? Yeah.
You've already kind of answered it, but you showed us earlier how this approach simplifies the calculation, but it doesn't seem like you were, like a student who followed this course would be able to identify what that calculation corresponds to in like an experimental setup or like physical effect. Was there some aspect of that that you?
Yeah. So in the tutorials and in the lectures, there was discussion of, what the physics is, or, what it corresponds to in the physical world. I wouldn't go as far as saying that the students can actually relate the formalism with the experimental setup, because that is not covered in the usual quantum information courses anyway, right? But they could know that there's entanglement, there's teleportation, there's a quantum state, and there were examples of how quantum states would be created or realized. So, for example, from optics. Yeah.
Is it, do you look at which part of this course, which contents the student is best compared to the usual?
No, not really, but it was already implicit in the questions. So there are some questions which are easier to do with diagrammatic. So if you have like lots of qubits in parallel, and if you are doing a quantum computation, you want to simplify the circuit, it's easier to do it with diagrammatics rather than by multiplying matrices and doing tensor products and stuff. So it was already implicit in the way the study was set up. So in this study, there was no Schrodinger equation, for example, right? Because it's not straightforward to do it. But that's a question for our future study in which we actually want to see which approach is effective to which kind of problems. Yeah.
So I saw on the, when you quoted like which questions,
Yeah.
a lot of them happen to be question 2. Is that like, because question 2 tends to be a particular type of question, and that would like.
Oh, interesting. That's interesting. Yeah. Yeah, so there were some topics that we didn't include in the study by design. So there was no discussion of non-locality, for example, right? I mean, even though material about non-locality is part of this book, but it was not in the study, right? I think like 60% of the material in this book was used in the study. So there was also no explicit discussion of probabilities. This is also something to test in the future trials. Yeah. Sorry. Yeah. Yeah, there were questions that were like too difficult.
Can you maybe repeat the question, because maybe the people watching remotely do not hear it.
Yeah, so sorry, could you rephrase it for me as well so that I can, could you repeat the question? Oh, okay, okay, I see. Okay, so the question is, in a university exam, there should be a bell curve of the grades. Too many students shouldn't get distinctions. I think that beats the point of this study. I mean, I know that in cases where there is no bell curve, some academics try to enforce a bell curve by applying some weighing factors. But I think, I mean, if we did that, then there would be no point in doing this study because we would always get a bell curve, right? We want to see the raw scores that the students get, Yeah. Yeah, exactly. So we were not interested in like designing the perfect course for an educational institution. We wanted to see how the students actually performed. More than half. Sorry, say that again. Yeah, that's the Oxford criteria. Yeah, but we also had, so 70 to 79 is distinction, 80 to 89 is high distinction, 90 plus is highest distinction. So I think that's a typical Oxford criteria. So we actually, I mean, the markers also use that criteria. It's actually in this paper if you want to have a look. Yeah. So by probabilities, I mean, of course, you need to introduce scalars and how the scalars interact and So all of this was diagrammatical. I mean, it's in the book, but this was not introduced in the course. The course was more about quantum protocols, circuit optimization, quantum teleportation, quantum communication protocols, and things like uncertainty, Stern-Gerlach.
More questions? No, let's then count again. Session is in half an hour.
Mute. We're good. Oh,
No, you have.
oh, it's, yeah. My bad. You good?
Just press any key and
Yeah.
it should work.
No, so people online hear you better in this area. So
Yeah, I'll go there, but just need the timer. So. Nick.
Cool.
Can you tell me?
When you have 5 minutes, yeah.
Cool, thanks. It's been a long day, but one more session, then the end, but yeah, great. So next we're going to hear from Max from the University of Hamburg, and he's going to tell us about surface diagrams for Verdier categories. And I think we have some props. You need to pass
No, I will pass them around during the talk. So thanks. Okay.
Thank you.
Yeah. So yeah, thank you for the invitation and thank you to the organizers for organizing this nice conference. This is joint work with my advisor, Christoph Schweigert, and the full title of my talk is actually Surface Diagrams for Frobenius Algebras and Frobenius Schur Indicators in Grothendieck-Berthier categories. And if you're interested in obtaining the slides, you can go to the URL at the bottom or scan the QR code here. But let's get started with the actual talk. So let me start by showing you a cartoon that outlines the aim of this talk. So here we can see a category theorist with, who studies rigid monoidal categories or monoidal categories with dual objects, so evaluations and co-evaluations satisfying zigzag identities. And the aim, and they study it using the string diagrammatic calculus for these categorical structures. And the aim of this talk is to go beyond rigid monoidal categories and look at more general duality structures, namely Grothendieck-Berthier categories. And Grothendieck-Berthier categories come with non-invertible coherence data. And this leads to the following slogan, which will hopefully become clear after the talk. So these coherence morphisms live behind string diagrams in the third dimension. And don't worry if you don't understand what this means. This is the aim of this talk. Okay. But let's begin with the protagonist, namely with Grothendieck-Berthier categories. And instead of throwing at you the full definition, let me start by presenting a motivating example. Namely, let's look at an algebra A over a field K and consider its category of bimodules. Now, this category carries a monoidal structure. This is the usual tensor product of bimodules. It's defined as the co-equalizer of these two pairs of arrows. And it's defined as a co-limit. So in particular, the tensor product is right exact. The monoidal unit is the algebra A itself. And Grothendieck-Berthier categories are some sort of duality structure, as I mentioned. So it shouldn't surprise you that from now on, we'll assume that the algebra A is finite dimensional, and we'll look at the category of finite dimensional bimodules over that algebra. Now, we have some sort of duality structure on this monoidal category, namely given a bimodule M, we can consider its k-linear dual as a vector space, and this becomes a finite dimensional bimodule via the action none. Now, taking a finite dimensional bimodule and assigning to it this k-linear dual bimodule, this gives a functor, and this functor is an anti-equivalent where its quasi-inverse can be chosen to be the functor itself. Now we have a monoidal category together with an anti-equivalence on it. So this induces a second monoidal structure. And explicitly on objects, this monoidal structure is defined as follows by this De Morgan type duality. And by definition, since D is an anti-equivalence and the other tensor product is right exact, this tensor product here is left exact. Okay. Now, we've described a monoidal category with some sort of duality structure, and it's a natural question to ask, well, what is the appropriate categorical duality structure on this category of finite dimensional bimodules? And the first attempt might be to say, well, maybe these are rigid monoidal categories. So we have evaluation, co-evaluation, satisfying zigzag identities. But I'm claiming that this is not the case, and maybe let's ask the audience whether anyone has a suggestion for a quick way to see that this is not true. Anyone with ideas? Okay. So
It's not going to be natural, right? The unit of the co-unit is going to fail to be natural, maybe.
Well, yeah, essentially the problem lies in the co-evaluation, if that's what you're saying. Yeah. A quick way to see it is that the tensor product of bimodules is generally not exact. And in a rigid monoidal category, the tensor product is always exact because it has a left and a right adjoint. Okay. So we need something more general, and it shouldn't surprise you. I mean, it's in the title of my talk that this will turn out to be a so-called Grothendieck-Verdier category. And let me now give you a full definition. So we have a monoidal category C with monoidal product O times and monoidal unit 1. And then we call an object K and C dualizing if it satisfies two properties. So the first property is a representability condition saying that for every object Y and C, the following functor, which is composed of tensoring with O times Y, and then considering the Hom functor into K, that this functor is representable. Now, representability implies functoriality. So by the first condition, we get a contravariant functor D on our monoidal category C, and we require that this functor is an anti-equivalence. And then we call a monoidal category C together with such a dualizing object. We call it a Grothendieck-Verdier category or a GV category for short. And you might know these monoidal categories as non-symmetric star autonomous categories. And these have been mentioned in Thea's talk before. Okay, let's briefly discuss examples. And or maybe let me say that, I mean, I'm using this terminology of Grothendieck-Verdier categories because this goes back to Boyachenko and Drinfeld, which they are more motivated by examples coming from algebraic geometry. And in Hamburg, everyone calls them Grothendieck-Verdier categories, and I don't want to be an outlier and be something. Yeah.
Are you also implicitly enriched over vector spaces?
I mean, I didn't say it, but yes, essentially I'm doing it. I mean, I'm more of a representation theorist, so you can assume that when I say monoidal category, I'm always talking about K-linear monoidal category.
Thanks.
And most of the time, it will be enriched over finite dimensional vector spaces. Okay, so the monoidal unit of a rigid monoidal category gives you a dualizing object. So any rigid monoidal category gives you an example of a Grothendieck-Verdier category. And the category of finite dimensional bimodules of a finite dimensional algebra also is a Grothendieck-Verdier category where the dualizing object is the K-linear dual of the algebra A itself. Now, you might have in mind a lot more examples. One example was given by Thea in her talk, but as Nick pointed out, I'm interested in representation theoretic examples, so I'll focus on that. And the main example, the reason why people in Hamburg are studying Grothendieck-Verdier categories is the following. So a large class of representation categories of so-called vertex operator algebras carry Grothendieck-Verdier structures. And don't worry if you don't know what vertex operator algebras are. You can think of them as a black box. There are some very intricate, difficult, complex generalizations of commutative algebras, and they appear in algebraic geometry and also in conformal field theory, and that's the reason why people in Hamburg are very interested in it. Okay, yeah.
Given the name, I'm wondering, like, the category of coherent sheets or a certain scheme you get out of it.
Yes, under some conditions, yes. So you can look in the paper by Boyachenko Drinfeld, they spell out various examples. Yes. A derived category, yeah. Okay. And also, if you look at generalizations of Hopf algebras, and now you look at something like a Hopf algebra in the category of finite dimensional bimodules, these are known as Hopf algebroids, and you require that these Hopf algebroids or these Hopf algebroids have an antipode so that they are full Hopf algebroids, then finite dimensional modules over them also carry Grothendieck-Verdier structures. Okay. So this is all nice and well. We have the notion of Grothendieck-Verdier category, but this definition didn't capture the second monoidal structure at all. And maybe let's try to find a formalism that encapsulates this second monoidal structure. And this was done roughly 30 years ago, and this was also mentioned in TSOC, namely under the name linearly distributive categories. And this was done by Cockett and Seeley in the 90s. And let me give you a definition. So a linearly distributive category, or LD category, is a category C together with two monoidal structures, O times N1 and R and K, and two natural transformations of the following form. You can think of them as mixed associators, and they are called distributors, and I will stick to that terminology, and they are required to satisfy a large number of coherence axioms. It was very important, these distributors are not required to be invertible. Okay, since they will become relevant later, let me discuss briefly these coherence axioms. So on one hand, we have 4 triangle diagrams. So the distributors have to be compatible with the uniters. Here's an example. So applying a distributor once and then a uniter should be the same as immediately applying a uniter. Then we have 6 pentagon diagrams. Again, here's an example. They show that they express that the distributors are compatible with the associators. And yeah, here's an example. So applying an associator and then 2 distributors should be the same as applying a distributor and then an associator. Okay. And now I hinted at this before. So my conjecture, well, we have a Grothendieck-Verdier category, then we get an LD category, and vice versa. This is actually not true. You only get a subclass of LD categories, and these are known as LD categories with negation. But let me treat this as a black box. But if you look at LD categories with negation, then you have a one-to-one correspondence between these 2 structures. And I will from now on use these terms interchangeably. Now, the first definition is good if you want to verify in explicit examples that one of these structures is present, while the right-hand side is quite relevant, as we will see, if you want to study algebraic structures defined internal one of these structures. And it's in particular important if you want to do then explicit calculations with them. Okay, but there's a problem. So if you look at LD categories, they come with a lot of coherence axioms. And this makes calculations often very difficult and tedious and bureaucratic. And let's remember how we dealt with this problem in monoidal categories. So you can say, well, we have Maclane's strictification theorem. So any monoidal category is monoidally equivalent to a strict monoidal category. So we can essentially neglect all coherence data. Unfortunately, this is not possible for LD categories, or at least for the LD categories that we're interested in. Namely, in most cases of interest, these LD categories have non-invertible distributors, and therefore are not strictifiable. And if you want to have a precise statement for this result, you can look at the work of Cockett and Seeley, and you can find a full proof of this in my bachelor thesis, where also it's made precise what is meant by suitably equivalent. Okay. Okay, so we don't have a strictification theorem, but maybe we have a full coherence theorem. So that we can also essentially neglect the coherence data because every formal diagram in our LD category commutes. But however, this is also not true. And probably people who've worked with LD categories, that shouldn't surprise you. You can prove partial coherence theorems. So what one can prove is if the distributors are split monomorphisms, then every formal diagram commutes. What we can also prove is that every diagram made of associators and distributors commutes. But if you incorporate the units, then you don't have full coherence. And you can build examples in the category of finite dimensional bimodules over this 3-dimensional algebra. Okay. So we don't have stratifiability, we don't have full coherence, but maybe we can save some sort of graphical calculus for Verdier categories or linearly distributive categories with negation. And the fact that we need to take care of the coherence axiom suggests that we somehow need to incorporate them in this graphical calculus. So we need to depict coherence morphisms explicitly. Formally, this can be done using the notion of surface diagrams, which I'll explain now. Okay, so we'll fix an LD category C, and for now, we don't require it to have come with negation, be an LD category with negation. Okay, by definition, C lives internal to the monoidal 2 category. Categories functors in natural transformations, and you can also look at enriched categories, enriched functors, and enriched natural transformations. Okay, and monoidal 2 categories admit a 3-dimensional graphical calculus, and let me now unpack what this means in this specific case. So for instance, we want to represent the identity natural transformation on the monoidal product on C, and the canvas for our graphical calculus will always be the framed unit cube, where the framing indicates the direction of composition. So the first arrow indicates the Cartesian product, the second arrow indicates the horizontal composition in our category, and the third arrow indicates the vertical composition. Okay. Now let's depict the source of this pasting diagram on top. Okay, this is done by juxtaposing 2 vertices at this edge. The target of this pasting diagram, and now for the bifunctor monoidal product at the bottom, is done by drawing a vertex on the opposite side, as follows. Now, the monoidal product at the bottom will become a vertex in between these 2 lines, connected by wires, as follows. Okay. Now we do the same thing for the monoidal product on top. And now we want to draw the identity natural transformation. This will become a vertex in between these 2 planes. And then this will sweep out a surface in 3 dimensions as follows. Okay. The identity natural transformation acts as the identity with respect to horizontal composition, vertical composition. So as you're familiar with from the graphical calculus for 2 categories, we can leave it away. So it's a transparent object. And the canvas will always be the framed unit cube, so we might as well not draw it. Okay, so this now depicts this identity natural transformation. This is the monoidal tuning fork by the shape of this diagram. That's why I call it that. Now we can do the same thing for the other monoidal product, and we now draw it in red. Okay, we can also depict the distributors. So these mixed associators, and the geometry looks as follows. Unfortunately, you cannot really see it, but this is a red. Okay, and here we have printed out a discrete system, homotopy.io. You can see the geometry, and maybe I can pass it around so that people get an idea. Okay. By reflecting along the side face, you get the other distributor. Okay. And what's important, I mean, I said we don't have full coherence, so we need to explicitly depict the coherence axioms. And this can be formulated in this graphical calculus as well. And these amount to changes of stratification. So we have here labeled stratified surfaces, and the coherence axioms become now changes of the stratification, which intuitively amount to moving sheets across the surface. So for instance, a triangle diagram, or the triangle diagram that we saw before, now amounts to taking this triangular sheet and moving it across the red functor line. Like here. And I colored this sheet in gray only for illustrative purposes, so this has no mathematical content. Okay. The pentagon diagram now also can be seen as moving the sheet across a vertex or across the surface. So the pentagon diagram is a 3-to-2 diagram. So we have 3 purple vertices, and here we have 2 vertices. And this amounts to taking the gray sheet and moving it across this vertex. Okay. So this is all nice and well, you might say, but can you do some actual computations with it? And let me start by some more or less elementary example. Namely, let's look at Frobenius algebras. And this was one part of the title of my talk. And first, let's look at the definition. So we define an LD Frobenius algebra in LD capital C to consist of a unital associative algebra with respect to one monoidal structure, the co-unital co-associative co-algebra structure with respect to the other monoidal structure, such that these two structures are compatible in some way. And these, I mean, the motivation for me and for Christoph to work with Frobenius algebras comes from conformal field theory, where in the physics paper, people have described essentially these LD Frobenius algebras without calling them that. I mean, they have appeared before in various works, but yeah, this was our motivation. Maybe let's not look at these Frobenius relations in one-dimensional notation, but look at them in the graphical calculus. Okay, so first, we want to depict the multiplication and co-multiplication. And in terms of pseudo-string diagrams, this would look like something here on the bottom, okay, where the black dotted line indicates the monoidal unit of our category, one, and the other one, the other monoidal unit. Okay. And now in the surface diagrammatic calculus, you see that from the front phase, we get the usual string diagrams that you're familiar with probably, but in the back, yeah, we have some sort of extension. Okay. And now we can describe these Frobenius relations in terms of surfaces. So first, let's look at the bottom. And here we have these pseudo-string diagrams, which are not really formal, but which indicate what actually should happen. So we have this compatibility between multiplication and co-multiplication. But here we have three wires appearing. So we somehow need to re-bracket, and this is there the distributor appears. So we explicitly need to depict the distributor because we are not strictifiable and not fully coherent. And this distributor lives behind the string diagram, and in the surface, this looks as follows. So maybe these are the surfaces so that you get an idea and don't only see these projections. So we can also pass this through. Okay, and it actually was, I mean, we looked at these surface diagrammatic calculus precisely to make calculations in these pseudo-string diagrams precisely. Okay, and maybe let's see, okay, from now on, I will drop the labels which indicate that we're using the O times or the Parmenoid product because we only have one choice. Yeah. No, that's intentional because I mean, A is an object in C. Well, equivalently, exactly. So it goes from the terminal category into C. It's a function from the terminal C, or if you want to work enriched from the unit V category into C. Yeah. And you can actually think of these diagrams as cut-off surface diagrams. So you can define Frobenius LD functors, which are where you draw lines on the distributor surface, which should be somewhere. And then if you cut along these lines, you get precisely these pictures back. Okay. But you can actually prove results with it. So you might be familiar from usual Frobenius algebras that the Frobenius relations are not independent. So one implies the other. And this also holds true for LD Frobenius algebras. Namely that if we require that this Frobenius relation holds, then automatically this Frobenius relation holds. Okay, and how does the proof go? Well, we first draw out the string diagrammatic proof for the usual Frobenius algebras in monoid. Then in our head, we think of them as pseudo-string diagrams. And then we extend them into a third dimension. Of course, there are choices involved, but we extend them in some way. And then we see, well, our proof is not completely finished. So for instance, we can't apply a Frobenius relation to this surface here, because we would have a distributor need to appear here, but there is no distributor. So we need to apply coherence axiom in order to apply this Frobenius relation. And we look at the geometry, and the geometry tells us, well, we just need to move this triangular sheet downwards in order to create a distributor, and then we can apply this Frobenius relation of one. So in other words, we need to apply the triangular coherence axiom that we saw before. And doing that, we'll fill all the empty spaces and we get a full proof of our result. And using the same proof technique, we can prove other familiar results from Frobenius algebras in monoidal categories and generalize them to Frobenius algebras in LD categories, abelian LD categories, or abelian LD categories with negation. Let me just mention one example for reason of time. Namely, for instance, one can show that if we are given an LD Frobenius algebra and an LD Frobenius algebra, then the category of left modules over the algebra is isomorphic to the category of left comodules over that coalgebra. And note that this is a non-trivial statement because algebra and coalgebra structures were defined with respect to different monoid structures. In particular, in the proof, of course, the distributors appear. And there are higher dimensional versions of these, of the string diagrammatic proofs that we saw before. Okay. Let's now come to the second part of my talk, namely at so-called higher Frobenius indicators. And don't worry if you don't know what this term means. And don't worry if you don't know what the sentence means. But what it says is that ordinary higher Frobenius indicators are invariants of k-linear, pivotal, rigid monoidal. I said that don't worry if you don't know what these terms mean. Of course, you should know what rigid monoidal means and what k-linear. The rest, hopefully, I'll explain in a second. Okay. But what we want to do is we want to generalize the statement to higher Frobenius indicators are invariants of k-linear, pivotal, and now multiplicative. So now let's unpack these terms. So a pivotal structure on a rigid monoidal category is some sort of trivialization of the double duality functor of a monoidal category. And what sort of trivialization? Well, it should be an isomorphism of monoidal functors. So it should be a monoidal natural transformation. We can more or less copy this definition to define what a pivotal structure on a Grothendieck-Verdier category is. Namely, a pivotal structure on a Grothendieck-Verdier category is an isomorphism of Frobenius linearly distributed functors. Okay, so the duality functor of a Grothendieck-Verdier category is not a monoidal functor, but it's also a functor with structure, and it turns out that it's something called a Frobenius LD functor, which is a suitable notion of functor between Grothendieck-Verdier categories. Yeah?
You got 5 minutes.
Thanks. Okay. And we can depict this natural isomorphism in terms of these usual string diagrams, not string diagrams, but usual graphical depiction. Okay, so rho is a natural transformation from the identity functor into the composite of the itself. Okay, and it has an inverse by definition. You actually don't need to require it, but let's not worry about this. So it has an inverse, and this is depicted by reflecting the diagram at the bottom of it. And relabeling, of course. Okay. Okay. And from now on, we fix the field K. We fix the K-linear pivotal Grothendieck-Verdier category, and we assume that the Hom spaces of that K-linear category are finite dimensional. Okay. And now we take an object V in such a category. And you can think examples are, for instance, category of finite dimensional bimodules or finite dimensional algebra, and also representation categories of perfect operator. So you can think of V as a finite dimensional bimodule over finite dimensional algebra. Okay. And now we want to define an endomorphism on this Hom space. So the Hom space of the monoidal unit 1 into the n times monoidal product of the unit itself with a certain bracket. So in other words, on this space of invariant instances. Okay. Let's first look at this in the case of pivotal rigid monoidal categories. So how would you, would be one way to define it? So in terms of string diagrams, well, we take the morphism from the monoidal unit into the tensor product of the unit itself, and then we bend around the leftmost string using them at this point that we can identify the double dual with itself. This is a definition in the case that our category is rigid monoidal or pivotal rigid monoidal, but of course it's not a definition in the case that we're interested in, namely in the more general case of pivotal Grothendieck-Verdier categories. But we can apply the same idea that we have had before, so that we extend these string diagrams into a third dimension, and essentially the geometry tells us where which coherence morphisms appears. And then we arrive at the following rather complicated picture. So we have a morphism from the monoidal unit into the par tensor product of the unit itself, and we map it to some complicated surface diagram, which represents also a morphism from the monoidal unit to the tensor product of V with itself with respect to the par monoidal product. And if we look from the front face, we get the usual string diagrammatic features. So modulo the monoid unit. So here we have the same picture from the front, and here also we bend around the string and derive the following picture. Okay, and now the Frobenius-Schur indicator is the trace of the endomorphism that we defined, or the powers of that endomorphism. And now we can prove surface diagrammatically various results. So for instance, we can prove that they're actually invariant. So that they are invariant under a suitable notion of equivalence between pivotal coordinates. And we can prove this surface diagrammatically. We can also prove, for instance, that these Frobenius-Schur indicators are one on the diagonal. Okay. And what would be very interesting is now to compute examples of Frobenius-Schur indicators, or for instance, finite dimensional bimodules or representation categories of vertex operator algebras. Okay. So I hope the slogan from the beginning, namely coherence morphisms live in a third dimension, now has become a bit clearer. So thank you for your attention, and I'm looking forward to your questions. Sorry?
You associate first.
Okay, yeah. I'll need to talk to Nick in order who gets how much.
And I wonder if you do this, this work I done and think I wasn't making about
Yes.
And the formalism is very similar to yours, but it's like the same setting.
Okay, so my understanding is that what they do is they look at Frobenius pseudomonoids in the monoidal bicategory as profunctors. So categories, profunctors, and natural transformations. And when they get different surfaces, for instance, I wouldn't know how to describe these Frobenius algebras in the setting. So we saw, maybe to illustrate an example, so what we saw is that this under Y and C was relevant in the definition of a coordinate. You can think of this as a profunctor, right? Where you look at the composite of O times with okay. And then you can just internalize the definition of coordinate. So define coordinate categories as representable Frobenius pseudomonoids in this bracket. Okay. But yeah, so this is their formalism, but I don't see how to translate between these two things, between these surfaces.
What you seem to be doing is having a sort of star autonomous structure inside of that. So it might be something like a microcosm principle thing, where this work is sort of extended in a paper by Bruce Bartlett and some other people, including Jamie, called modular categories as representations of the three-dimensional orders of two category. Where they take this approach and then they define a kind of internal string diagram calculus where they think of these string diagrams as defining tubes with space, and then inside the space that's like a place to have string diagrams, but presumably your string diagrams might be living real surfaces.
Okay, so you're saying that you can translate the pictures I have?
No, I think it's happening at two different levels.
Okay.
Timo?
Yeah, you mentioned that you prove by reason of the surfaces.
Yeah.
How do you do that? You practically do that when you're living on the PIO, or do you have fun on ways to prove that, or it's just like you really nice things on today class?
I mean, I draw it on some sort of tablet, and then I copy the surfaces and I look locally what movement corresponds. And I implemented certain, not proofs, but proof beginnings in homotopy IO, but it turned out quite difficult to implement complete proofs in homotopy IO. Sorry?
Homotopy IO doesn't really let you do it.
Yes.
Which version did you use to use the beta
Beta
version?
version, yeah. But you can play around with it. I mean, there's homotopy IO, there's some files on our website where you can download the signatures.
Okay, so the polymers are just like looking at the thing and using your brains to match the original condition that you have.
Right.
Well, you would come up with
I mean, to me, it's not that different from string diagrams. I mean, of course, you can say it's. I mean, we're working with projections, but yeah.
Sure, it's not that different than string diagram, but it works with like 4D.
Yeah, sure. But I
Anyway,
didn't need to work in
there's
4D.
a-
Yeah, of course.
Question from Mario.
Yeah. Thank you for that. So I wanted to ask you, when you say that you know the string diagram that you call to search it diagram.
Yeah.
Because apart with the hard side, where you're reading, like.
No,
For any pseudo string diagram, there could be multiple.
indeed, and we saw examples before. So we drew out the string diagrammatic proof of the Frobenius relations are not independent. And then we saw that there were some spaces in between that were missing. And if you look at the front face, then it corresponds to the same pseudostring diagram.
And is this the case in ordinary two-bit category?
Sorry?
Is this the case for ordinary two-bit category?
Yes. I mean, this is essentially a calculation for linear distribution. Yeah.
Thank you.
Yeah, thank you.
Great. Let's thank the speaker again. So my pleasure to welcome Amal, who's going to tell us about diagrammatic infinity n categories.
Thank you. This is a joint work with my student, Clémence Renava. And about a year ago, there was a workshop on infinity n category. I think it was the first workshop on actual infinity n categories. And my colleague there that I hadn't seen for a while, and he was he was not at the workshop, he was just working at that university. And so I met him in the corridor and he asked me, well, what are you doing here? So then I was like, well, there's a workshop on infinity n categories. He was like, haha, like, what a workshop on infinity n categories? Like, do you guys even know what the definition of infinity n category is? And yeah, it's like then. Of course, I know what an infinity n category is. I know an infinity n category when I see it. But in fact, like since then, that's kind of the question that people have kind of asked me the most, like people who are not in the kind of high category world. Like it's been a meme for a long time that kind of weak high categories are like an idea and search for definition. And but of course things have evolved and they've changed in the last decade and more. So but anyway, I thought that because I get asked this for a long I get asked this a lot of time, I would do a talk which is basically mostly an introduction of what the state of the art is about infinity n categories and their models, and then at the end I will tell you a little bit about what Clémence and I have been doing in the hope that at least you can then tell others that things have changed. So, I mean, in some ways, I would say that it's still the case that infinity n categories are primarily an idea and only secondarily a definition or a network of definitions. So what we kind of expect of what we have always been expecting about infinity n categories is that it's something that should generalize many things at once. So these are some of our desiderata. We know that we want infinity zero categories to be precisely infinity groupoids, and that's kind of established what an infinity groupoid is. It's like classical multi-p type, CL multi-p type of CW complex. Well, we know that we want infinity one categories to generalize categories. And we want infinity two categories to generalize by categories. These are other definitions which are very well established, and we know what they are. We know that we want to have this sort of inductive thing here, where an infinity n plus one category between any 2 points or objects or zero cells, whatever you want to call them, it should have an infinity n category of cells. Well, I would say that by now also the notion of infinity n one category is perfectly well established. Ever since, since the work of Lurie and everything that kind of followed from it. And infinity one categories are also, thanks to Lurie, often called just infinity categories. So this is why we're stuck with this infinity and infinity terminology. And finally, well, we do have a notion of strict n category, which is the kind of the earliest kind of notion of entirely directed n category that has come, and it is kind of commonly expected that, well, infinity n categories should also be a generalization of strict n categories, and in the sense strict n categories should be some kind of subclass of infinity n categories. I actually think this is a bit more complicated. I certainly strict n categories can be a source of infinity n categories, but I think it's still a bit dodgy whether strict n categories should be a subclass of infinity n categories. And then a question, okay, if we want to produce a model of infinity n categories, what should a model consist of? Like, what are the data that we need to give to? And because again, it's not something that's it's not a precise definition of what a model is. It's just like what you can extrapolate from what is considered a model, and extrapolate what are the data that you need to present. So first of all, you need a model of what K cells are for each K. So that is a kind of object made of cells of various dimensions, possibly of any dimension up to infinity. You need to have a model of what kind of structural homotopy exist between cells. So there's going to be some kinds of ways to transform cells or diagrams of cells which are just part of the model. This can include things like units or these kinds of various coirators, but there usually is always some kind of structural part that's not part of a specific example, but something which always exists. Then cells in an infinity n category in general can have this direction. They're not like all homotopies. They can be non-invertible. So we should have a notion of what cells are actually equivalences, the ones that are invertible in a suitable sense. And in the case of infinity n categories, we expect that all K cells for K larger than n should be internal equivalences. Then we need to have some kind of class of diagrams which we consider to be the composable diagrams. So arrangements of cells which we consider to be composable. And then, given such a composable diagram, we need a notion of what it means for a cell to be the composite or a composite of that composable diagram. And finally, this is all about single objects, but we also need a notion of what it means to be a morphism on infinity n categories. So we need a notion of functor. And among those functors, we also want to have a characterization of the functors which are equivalences or weak equivalences. So we want to, exactly like when you present some mathematical object that lives in a category, we want to know what it means for two objects to be isomorphic. Here we want to know what it means for two objects to be equivalent. Okay. So just as an example of a kind of stupid instantiation of what I've said, let's see what it means for categories to be a model of infinity one categories in this sense. It's a degenerate model. It doesn't model all of them, but it is a model. So what are the cells? Well, they're either objects, or they're like either points, or they are arrows, or they're morphisms. So there's two kinds of cells, and there's no k cells for k larger than 1. And what are the structural homotopy that exist? Well, the only one that exists are identity one cells. You can see an identity as being some kind of homotopy, which always some kind of one cell which always exists on top of every 0 cell. What are the internal equivalences in a category? Well, there are the isomorphisms. They are the invertible cell, the invertible one cells are the isomorphisms. What are the composable diagrams? Well, we can compose a chain of morphisms. So the composable diagrams are all the ones that have these kinds of shapes. What does it mean for something to be a composite of one of these diagrams? Well, we have an algebraic notion of composition, right? So we have something which takes something shaped like this, and it gives us a single thing, and then we say that, oh, this is FG, this is the composite if our operation of composition gives us that composite. Functors are functors and equivalences are equivalences. What kinds of models exist? This is a very rough classification. One first kind of thing that you can ask are, so we've got these kind of things that we have specified, structural homotopies and the composites. So the question is, are these determined explicitly by certain operations? Like in the case of categories, yes, composition is an operation, the unit, taking the unit on a 0 cell is an operation. Or maybe these things are just somehow asserted to merely exist. The answer is yes, the determinant of operations, we've got an algebraic model. If the answer is no, we've got a non-algebraic or geometric model. And then this kind of is really, it's mostly just about the algebraic models, but what we can ask in general. The question of, does composition satisfy any non-trivial equations on the nose, so not after some equivalence? If there are non-trivial equations satisfy composition, we have a semi-strict model. If it does not satisfy any non-trivial equations, we've got a weak model. So you can kind of try to put models on a kind of chart with 4 quadrants, semi-strict, weak, geometric, algebraic, and this is a kind of rough picture of what the landscape of models is now. It's incomplete, certainly, but I would say that the most kind of well understood and used models are in this geometric weak quadrant. And the mainstream class of models that most people actually using thin categories now are these seagull type models. There's this other class of models, which are shape models. You can think of these as coming from the seagull type models, come from trying to generalize the definition of categories as having objects and then homosets between any two objects. Whereas these kind of come from trying to generalize the definition of categories as graphs together with the composition operation. And then we have quite a few algebraic weak models. We have some which are based on a kind of formalism of globular operats. And then we've got some more recent models which are formalized as type theories or mathematical semantics of type theories or generalized algebraic theories that Thibault here and others have worked on. And then there's strict and categories, obviously. And then in yellow, I kind of I've noted the things that myself and Clemens are working on. So what we worked on is a weak geometric model called the chromatic model. And then there's this work in progress on a semi-strict algebraic model, which we call chart and omega categories, which is currently it's a definition which is well defined after conjecture. So it's not, this is why I've written it in this kind of dashed thing. So it's work in progress, but it's where we're kind of trying to aim for. And then there's the question, okay, there's all these models. Are they all models of the same thing? So when are two models equivalent? Well, the gold standard of equivalence at this moment is to use this model category theory. So it's about defining a model structure on some category of these, on some category, where the infinity n categories are going to be bifibrant objects, and such that weak equivalence between bifibrants are going to be the weak equivalences of infinity n categories. And a certain subclass of morphisms between bifibrant objects are also going to be the functors. And then once you've done that between two models, the standard for equivalence is to establish equivalence of model categories. That's the kind of the best type of equivalence people have been proving for now. It's not yet the best thing that one can do, because it's only about characterizing kind of the high structure, like the invertible high structure. It doesn't guarantee, for example, that you have the same notion of kind of lax natural transformations or things like that. That is the best that we have right now. And so what is the situation for that? So here I've drawn with full lines. I've drawn the models which have been compared to the best standards after full and equivalence. So here we have this kind of nice cluster. This is quite recent work by mainly Félix Roubaton, also relying on work by Osorno and Ravelli. So here we have a nice cluster of models which are really actually equivalent to best standard. And then if this is well defined, we have actually proven that our weak model is equivalent to the, like up to this conjecture, we are able to prove equivalence between two models. This is kind of the thing that we've been aiming for, because it would be the first result actually proving an equivalence between an algebraic semi-strict model and, well, between any algebraic model and the weak geometric model. And then there's a kind of nice cluster here in the algebraic world, but the kind of the homotopy theory of these things less well understood. So usually these things are kind of object-wise, or maybe at the level of categories where the functors are all strict. So it's not quite the best standard. And well, the strict model, it is actually disproven that it is equivalent to these. So we know that the strict model is not good. And only in the case n equals 0, I don't know if you see this, purple is not very visible. We also know that our diagrammatic model is a good model. That's also in infinity. So all the infinity groupoids for all these things are the same infinity groupoids. So this is so they satisfy this homotopy hypothesis. We still don't know about high dimensions. This argument seems to work also for n equals 1, but not the same argument does not work for high dimensions. But basically, so far, any model that's kind of failed to be equivalent to others has failed already for n equals 0. So if we were to discover that this cluster is not equivalent to this cluster for higher n, it would be interesting new mathematics. It wouldn't be it would mean that there's possibly different plausible notions of infinity n. Yeah.
Sorry, does this object-wise thing mean that the one categorical shadow admits an equivalence of categories? Is that, or do you mean something else by this?
I'm not actually completely like these results I don't know them very well, but I know that there's no kind of molecular autostructure, and I think there's also no I think notions of weak functors have only been studied in, I think, these models in some work by
Right, so
John Bolt.
it's like the homotopy theory has not been explored, but not explicitly disproven either.
No, it hasn't been. Nothing has been disproven. It's just that it's not as well developed. And I think the equivalences are really at the level of, yes, these model the same algebraic structures. So now a more kind of a softer question. How does it feel to be doing infinity and category theory nowadays if you are an infinity and category theorist? Well, if you look at the kind of papers that use the mainstream models that I'm talking about, it's a kind of different subject from, say, two-category theory, which is it's not true for the infinity one case, because that's like one of the reasons why people have been enthusiastic about finite-Hoppus theory is that there's been a wealth of kind of one categorical techniques that have just work in the infinity one world. I would say that currently with infinity and categorical models, the models tend to be not self-contained. Basically, you take some kind of very simple construction, I don't know, I take the slice category, and instead of kind of remaining within the same model, it takes you into some other model, and then there's some, you know, the way that people reason is that they're constantly using the kind of network equivalent functors to be able to say that, oh, this is a different thing, but it's actually kind of equivalent once you. So it's very different field to, like, yeah, imagine if every time you had to do anything with categories, you got something which is not a category, but so what, and I think, I mean, people are aware that this is a bit of an issue and it doesn't help with adoption of high category theory. And the usual answer in a kind of community of homotopy theorists and algebraic geometers is that, well, we should just work synthetically. So we should kind of change our language in a way which is kind of becomes model independent. So instead of working inside a model, we are kind of doing something like univalent homotopy type theory, where everything is equivalence invariant. Whatever I can say in this language is independent of equivalence. And this may be a kind of paradise for homotopy theorists, but I feel that it doesn't work for us. It doesn't work for us. It doesn't work, I think, for people like Max, like representation theorists and low-dimensional topologists, because we like to work with explicit diagrammatic presentations, and this is exactly the sort of thing, this sort of syntactic approach where you. And what you can't do here is just say, yeah, I want to construct a very small example of an infinity two categories generated by these data. This is exactly the thing which becomes kind of really impossible to do here. And so these kind of things do not have any kind of soundness for diagrammatic reasoning or anything like that. Maybe they don't care about it, but I care about this. And so what we're trying to do with Clemence is build a kind of, instead, not give up on having a self-contained model. And so this is the diagrammatic model we developed. It's the main kind of thing that we've been striving for is to have something which is closed under all these most important constructions, like building high functional categories, slices, grade products, joints, all these sorts of things that people want to do with high categories. They are kind of easy to define in our model and stay within the model. And it's also something which, by the way, it's kind of designed, it has an inbuilt diagrammatic language, so that basically diagrammatic arguments that are already being done for, I don't know, by categories can be easily adapted, so they become sound arguments that also work in every infinity two category, up in, like, by replacing equality with equivalence, essentially. So I'm going to just briefly try to tell you about some of the ideas behind this model, going through those points that I showed before. So our model of cells is based on a kind of combinatorial topological theory. I've written a whole book about this, for combinatorial categorical diagrams in the archive. So this theory of atoms, molecules, and regular direct complexes, which are supposed to be interpretation of certain shapes of diagrams. And this theory allows us to paste together cells to form, like cells are more complex than just globes or syntheses or stuff. There's more of them, but they can be still pasted together as in globular pasting for pasting diagrams. And this pasting in fact satisfies even kind of all the strict equations. This doesn't mean that the model is strict at all. This is saying that we can form pasting diagrams strictly. Our structural homotopes are specified by morphisms in a certain category atom, which is the symbol. They're specified by certain morphisms there, so the pulling back along one of these morphisms creates these homotopes. And the underlying structure of an infinity-n category for us is a free sheet over this category of atoms and Cartesian maps. What is an internal equivalence? Well, cells in a dramatic set, they're an instance of a more general notion of what we call a round diagram. So a cell is just a single thing, a round diagram is a particular kind of pasting diagram. And the nice thing is that this kind of combinatorics is rich enough that we can instantiate this notion of co-inductive weak invertibility or pseudo-invertibility that's been studied by Virginia Cheng, Alex Rice, and others. We will instantiate this definition at the level of round diagrams and then say that the weakly invertible round diagram is an equivalence. And in particular, a cell is an equivalence if it's a weakly invertible. And this is the reference of both this work. And then our class of composable diagrams is going to be exactly the round diagrams. And so this means that not every pasting diagram that we can form is composable. So there's a difference compared to strict omega categories or these globular models where usually whatever you can paste, you can compose. Now here you can paste things which lead to non-composable things, but every such pasting can be padded with some of these structural homotopes, and this can be done in a simple systematic way and turned into a round diagram. And then, as I said, this is a weak geometric model, so we don't have an operational composition at this level. But instead, we say that an infinity-infinity category is precisely the dramatic set such that for every round diagram, so for every composable diagram, there exists a single cell that you can treat as a weak composite and an equivalence one dimension higher, so some cell or round diagram one dimension higher that goes from that diagram to that cell. So you can, because this kind of relation of the existence of an equivalence is in fact an equation, equivalence relation and congruence. You can see it as saying that for us an infinity-infinity category is exactly a diagrammatic set in which every round diagram is equivalent to a single cell. So one in which you can reduce a diagram made of possibly many cells to a single one. A functor is just a morphism of the diagrammatic sets of the underlying free-sheaves. And it isn't, these things are somewhat called the omega equivalences. They are the functors which are essentially surjective on cells of every dimension, in the sense that on 0 cells you get essential surjectiveness up to equivalence. Then on 1 cells you get a kind of essential fullness on all the 1 cells between the same 2 objects. On 2 cells you get a higher version of essential fullness, and so on for every n. These things are called omega equivalences. And one of the things that happen in high category theory that you being an equivalence is all about surjectiveness, and because injectiveness becomes a form of surjectiveness. So our main results that are in our latest paper, model structures for diagrammatic infinity-n categories. Well, again, we can, so our kind of definition is natively, unlike most of the other definitions, kind of natively directed in all dimensions. So if you don't specify anything more, you have possibly non-invertible cells in every dimension. But we say that something is an infinity n category when all cells higher than n are equivalences. And then indeed we get a model structure in this category of diagrammatic sets whose biprivate objects are the infinity n categories. And this includes n equals infinity, by the way. And the weak equivalences between biprivate objects are exactly the omega equivalences. So it's it has the features that we want. And finally, as I said, in the case n equals 0, we are able to kind of show directly in a way that if this is simplicial sets, this is diagrammatic sets, we get this triangle of the junctions, and if we put this infinity 0 with regard to the model structure, this is infinity groupoid one, and we put the classical equivalent model structure of spatial sets, which is a canonical model, multiple types nowadays. Then all these things become equivalences, and this is this I would say kind of advances the state of the art, because it's the first time at least we know that there is a kind of proof the hypothesis for a model where indeed the infinity groupoids are defined as kind of high categories where all the cells are weakly invertible. In all other models that satisfy these, there is a little kind of sleight of hand in that there is somehow the model is already built upon a certain model of infinity groupoids, whereas here everything is kind of purely algebraically given. Yes?
Is that Canquillan twice?
Both of them are Canquillan, yeah. Well, that's how I say both, yeah. This is
That's just like
this is barycentric subdivision, which is a Can X functor, which is a kind of self-equivalent equivalence. Yeah. And yeah, I'm gonna stop here. Thank you.
I have many questions. I'll start with one of mine. So thanks for the great talk, as always. So you talked about how you hope that this could be like in essence, a usable model of infinity n categories. So I think one of the great successes of quasi-categories, infinity 1 categories, are that there is essentially an embedding from categories into quasi-categories such that what that means is every sort of one categorical argument has sort of an analogous thing in quasi-categories, so long as you sort of pick the right argument. But it's not too hard to sort of extend it along. And this really stops being true when you move to the world 2 categories. So does your model of diagrammatic sets, how does it sort of feel in the ergonomics with respect to that sort of thing?
So yeah, I would say that, well, what we have, for example, that is that you can actually embed the category, like you can embed even the category of bicategories and strong functors between bicategories. You can embed it into the category of diagrammatic sets, and its image lies in the infinity 2 categories, for example. So like literally up to bicategories, you can consider bicategories really as a kind of special case of our infinity 2 categories. And so in this sense, like most kind of formal category theory arguments are kind of immediately applicable to our model of infinity 2 categories. So I would say that that's like, you know, the formal category theory. So the part which is kind of diagrammatic, and that embeds, i.e. Because this is a shaped model, it's a bit maybe more awkward to think about the kind of the enriched category theory part. Typically, there's this kind of balance because as I said, shaped models kind of sort of generalize internal category theory, and the SYCO models kind of generalize enriched category theory in a certain sense. So again, I would say the kind of formal category theory usually is more about like internal to categories somehow, and so I would say that this is going to have an advantage for that part. It's a bit early to say whether you can.
Morgan?
So you mentioned earlier in the talk that you didn't expect strict things with inside the categories. I haven't thought that high up in the categorical hierarchy, but what's the obstruction of thinking of strict things as a special case of weak things, or what's the obstruction to strict anything living in?
So the way that currently strict things live and the weak models, wherever they do live, it's always through some kind of nerve, right kind of nerve functor. And these kind of somehow they give you some object which does what it should, but they don't deserve any kind of algebraic structure, because for example, if you have some category or n category which can clearly generate the is usually something that can always be the right hand on PLC coordinates. So it's known that a bunch of these coordinates, even homotopy coordinates there are no longer homotopy coordinates once you take this. And but people still, I think it's usually being assumed that this is just a kind of artifact somehow. But in our model, it kind of shows up that actually there is a kind of output structure. If you look, there is a kind of multi theory of strict hand categories. We have a kind of multi theory of infinity hand categories. We have an adjunction strict hand categories, which at n equals 4 stops being equivalent. And there's it's a bit of a long story, but it's something that only really showed up in our model for a bunch of reasons. In a way, because people were not working on it. That's something why I shouldn't try.
Great. Well, I think we should move on to the next speaker. So let's thank Amar again for the talk. I'm happy to introduce Thibaut, who's going to talk about naturality for high-dimensional path types. Right, we'll take it away.
Okay, so thanks a lot. And yeah, so I'm mostly going to continue the topic of higher dimensional categories and maybe infinity categories. But since I'm the last speaker of the day, I'm assuming that by now you've forgotten everything that you know about category theory. And so I'll start with very low dimension stuff and hopefully the stuff that everybody knows. But I really want you to have that in your working memory to understand what I'm going to say right afterwards. So first, let me recall what a functor is. So a functor is something that acts on objects of a category, and then it acts on morphisms. So if I have a morphism, I can take the image by the functor. And then there are some equations. I'll completely ignore the equations for the talk. Now, what is a natural transformation between two functors? It's something that acts on objects, and now to an object, I'll give a morphism, and it acts on morphism, and to every morphism, I'll give a commutative square, where the legs are given by the action of the functor of morphisms. That's it. Well, you may know something that two categories are like categories enriched in categories. And here you can like expand a little bit what those things mean. So a consequence of that definition is that the composition is a functor. And so what do we mean by that? Well, composition acts on objects. So if I have two cells, I can compose them. But composition acts on morphism. And what is a morphism? In the home category, well, it's a two cell. And so what I'm saying by saying composition acts on morphism here is that I can, given a thing like this, obtain something that goes from the composite of the top thing to the top of the composite of the bottom thing. And let me call that whiskering, just so that I have a handy name for the rest of the talk. I can also do it on the other side. That's just because that's how Cartesian product works. And since I'm not talking at all about the equation here, everything I've said here, you can also have that in bicategories if you want to. Only the equations will change in bicategories. They will be up to ISO. Okay, so what is a bicategory? Well, it's a weak two category, or a category where everything is like holds up to natural isomorphism. So, for instance, things are not associative, but there is an associative natural transformation that does something like this. It moves like that. And so what does it mean? Well, there's an actional object, which looks like a two cell that reassociates stuff. And there's an action on morphism. And now I'm cheating a little bit, drawing this as a one-dimensional thing, but really it's a two cell. Hopefully you can read what it is. And I'm only gonna talk about the one on F here, but there's similarly one on G and on H. Right, so that's our entry point, and that's the story I want to generalize today in one particular model on one particular model of infinity categories that I will call weak omega categories. So apparently it's not possible, it doesn't go away. Okay. I've been told that it
Click on the white.
No, you're fine.
Oh yeah. No, thank you. Everything works. Okay, so just to be clear, I will talk about the upper right corner of Amar's diagram. So the one that are algebraic and completely weak. And the underlying geometry is completely globular. So globular means that I can only consider higher dimensional cells between things that are parallel, things that have the same source and target. So a arbitrary kind of globular set, which is a generalization of a graph, will look like something like this. I want to impose that there exists some composition operations that will generalize the one that I've just talked about, some rules that axioms that need to be satisfied, and everything should be weak. So up to a higher dimensional cell that witnesses this equivalence. Okay. So I'll kind of zoom in the upper right corner of the diagram, and I'll talk to you a little bit about everything that's been done in that kind of space. So there is this cat here, which is the dependent type theory model, which is the one I'm working the most with, but it will not be extremely important for today. There's another one that was introduced recently by Dean Finster, Mark Elkis, Rutter, and Vickery, which is a definition of computers. If you know what this is, well, that's good, but it's not very mandatory. Then there is the Grothendieck-Martiniotis approach, which defines something called a coherator. And actually, this is not a definition, but a family of definition. Like you have a bunch of definitions. For every coherator, you have a notion. And to answer your question, Nick, exactly, what I proved at some point is that this type theoretic definition is equivalent, as in the one category of them are equivalent for a specific choice of coherator. And a good conjecture would be that the choice of coherator does not matter up to Quillian equivalence. But this is something we don't know. This is something we hope. Yes?
Do we even know what the equivalence means for the full picture? wouldn't be equivalent equivalence, right? It would be even.
No, yeah, but we don't really know. We don't even know equivalent equivalence.
Sure.
But so then there is like a similar result that was proved for the computers and something called globular monads that is developed by Batten and Leinster. Then Ara and Burke have proved that those two things are equivalent, and we've also made the connection here. So we can have, yeah, we have a nice net of things that we know are kind of look like each other, they behave like each other. It's good, but it's like we're working hard on relating them to the rest of the literature. Okay, so I will now try to give you a rough idea of what this model is and what it feels like to work within this notion of category. And here I'm giving a simplified version, so I'm not really distinguishing the approaches. I'll just give a rundown that kind of combines everything in a way that makes it hopefully more approachable. So the first key idea that I think Amma already said is that I want every composable situation, like if I spot something that's composable, to have a composite. So what do I call a composable situation? Well, if I have an X here, I want that to be a morphism from P to X, where P is one of those pasting schemes. And I'll explain what I consider pasting schemes, which is not exactly the same notion as Amar, but you know, we don't really have different names. So, and what I'm calling a composite is a morphism from. So here, where I'm writing D is like a disk. So a disk is like a representable thing, and by Yoneda, this is just like a cell in X. But it's very convenient to see it like that. So whenever I have a composable situation, I want a cell that is kind of the result of that composition, is what I'm saying here. And the second idea is that if I have two composites for a given composable situation, well, they should be weakly the same because my composable situations are kind of non-ambiguous. And by weakly the same, I mean that there is a higher dimensional cell that relates them in some way. And maybe that cell is invertible, but that's a different story. Okay, so let's talk about those pasting schemes. So for me, the pasting schemes are just globular sets that completely live inside the globular sets, and they represent the things that can be composed within globular sets. So some example, well, if I have two morphisms like this, hopefully you expect that this is a situation that can be completely composed, and that's a good situation. But if I have something like this is also a good situation. It makes sense to consider this entire thing and compose it completely. Some non-examples now. If I have something like this, where it kind of loops on itself, you would expect that you can compose it in some way, but it's kind of unclear what you mean by that, because like, do you mean going around or going around and then back here or something like that? It's ambiguous, and so we don't want that. This is like a bad situation. Well, obviously, if I have something like this, things are directed to that situation. And if I have a hole here in the middle, then it's not composable anymore because it's just not connected. Okay, and there are plenty of descriptions of those. Maybe the most used is something called globular sums, but you have like Batten trees and big words and everything that's kind of like Catalan-like. Okay, and let me now try and introduce those composites. So whenever I have a omega category that's kind of freely generated by this space by some of this spacing scheme, and I consider something of dimension n, well, I should see P as a composable situation inside of itself, right? More exactly like that, so I have like the identity morphism that goes from P to P. And what I mean by it should have a composition is that, now I'll be a bit more precise, is that for every possible choice of a way to compose its source and of a way to compose its target, I should have something that goes from from this choice of the source to this choice of the target. So I'm calling U and V the choice of the for the source and V the choice of the target. Then I should find a composition from U to V. And for the purpose of this talk, I'll denote that as comp P U to V. And you should think of that as the cell in P that witnesses the fact that I can compose P in such a way that I go from U to V. Right. And now if I have any two cells, U and V, that compose P, and that are parallel, because that's, I will need that. I mean, otherwise what I'm going to say doesn't make sense. But if I have any two cells that compose P, they should be related. That's what it means that the composition is like essentially unique or weakly unique, if you want. And so I'll denote co P U to V this for the purpose of this talk, this higher dimensional cell that goes from U to V, where U and V are two cells that compose P. Okay. So now, if I have a weak omega category X, and if I have a composite, like a composable situation, so a morphism from pacing scheme into X, I can find a cell in X that witnesses the composition. That's just the composite of those two arrows, right? And I'm gonna write that as comp P U to V bracket F. Just because it's gonna be convenient for me. And the same way, if I have two ways of composing the same composable situation inside of X, I can relate them by pre-composing it with this arrow that I've built. And again, I'll introduce similar notation for that. And essentially what I've done here is I've given you the definition of what all of those definitions of weak omega categories are, but without really going into the details. But like, if you look at them, that's exactly what they are telling you, and nothing different. Okay, so now let's go back to our story of what it meant for the composition to be a functor in a two category or in a bicategory. So recall that the composition is like, well, it's the composition really. And being a functor means that I can, in the context of a bicategory, means that I can replace the first argument by a natural transformation instead. Well, I kind of can do the same thing in weak omega categories. So if I take C to be this, it should be comp here, not co, my bad. But if I take C to be this composition here, well, I'm allowed to do by the kind of gymnastics that I've showed you just before. I'm allowed to introduce this composition here, it should be a comp here as well, where I replace the composable situation that's here, so this spacing diagram by this spacing diagram. And now I say that I want to go from the composition of this one, where I'm using F and G, to the composition of F prime and G. But like, this is the same thing that I was doing here. I'm just changing the star in a C here. Hopefully that's fine. Okay, so let's try and see the general picture. So I'm gonna have a composition and so sorry, let's try and see the general picture. And first I'll talk a little bit about what I'm doing on the pacing scheme. So I'm going to choose a pacing scheme P, and I'm going to choose X to be a set of maximal dimensional positions. Well, as an illustration here, I'm just choosing the previous pacing scheme, and X is just the set of like containing just F as the maximal dimensional position, right? And what I'm going to do is I'm going to call like this P up arrow X the same P, but where I've bumped up the dimension of that one thing that I chose, or those things that I chose to be in X, by 1. So here, instead of having like a one-dimensional thing here, I'm going to bump it up by 1. And I'm always going to denote that F minus, F plus, and F arrow, the thing that relates them. Does that make sense? Okay. And now I need also one more thing, is that there is always an inclusion from P to this P up arrow X, actually two inclusions, one that sends every selected things to their minus version, and one that sends every selected things to their plus version. Okay. Right, so now if I choose a composition, that's like, let's call it C primes, comp P U to B, it's the generic form of the composition, and a set of maximal dimensions inside of P, then what can I do with that? Well, I'm giving you an example here, which is just the example of the composition as before. But I can define this C prime up arrow X, which is now a new composition of a new pacing P. And oh, sorry, this is not, this is like in minus and in plus. Yeah, it's a little bit more. Yeah. But so I can define this new composition of this new pacing thing that I've built here, P. And I'm going to use my C prime, that's the composition I started from, and I'm going to substitute every tagged variable, every marked variable by its minus version in the source, and substitute every tagged variable by its plus version in the target. And this is exactly what I'm doing here. So I really recover the fact that the composition of one cells is functorial this way, or at least part of the data that made it functorial. And I've done that kind of in a general way for compositions here, but I can extend that to arbitrary terms in the theory of omega categories. That's not too hard. That's just like inductive and a bit tedious to do. So I don't really want to go into that right now. Yeah, but like hopefully you can see that this really matches the idea that we have like something and we can make it act on cells or higher dimensional objects instead of what it was before. Yeah, right. And so this is something I had done during my PhD, and this is really not too hard to do. But recently, with all of those people that were indicated at the start, we generalized that to talk about something that looks a little bit more naturative. So first, remember that I said like, oh, we have these compositions kind of things and also coherences like kind of things. And then I went on about talking about functoriality and a way to make everything look like it can act on morphism, but I just talked about composition there. So what about coherences? Why didn't I mention coherences? So let's take an example of a coherence, and I'm taking the associator here. So here, again, I'm noting the composition with a C, so it becomes a bit unreadable, but hopefully you can just see that it's just reassociating stuff. And I'm going to choose just F to be my set of maximal variable, and I'll just try to apply the same recipe. Now, what I want is something that goes from this A minus to A plus, but I'm blocked here because those don't really have the same source and target now on parallel. So I'm not allowed to assert that there should be a cell between them. However, if you stare at this long enough, you can see that the difference between this and that is just this minus here that has become a plus. But I've just told you how to change a minus into a plus. That's the functoriality part of the functor that was before. And so we can like insert the missing part here, where you have this entire term here that I will do the functoriality part with respect to F. And that will give me an arrow from the minus version to the plus version. Same on the other side. And now this A of arrow X here, I want that to be a filler for this square instead of being a filler for a thing that's kind of a bubble. And so this looks really like very much like the naturality square for the associator that I had given you in the very beginning. Except that now I'm choosing a cell here which is a higher dimensional cell, and that's not just like an equation. But I could also choose a cell in the other direction.
Sorry,
but
upper
yeah.
right corner should be an F minus.
Oh yeah, sorry, my bad. This sorry. Yeah, this is F minus indeed. Yeah, sorry. Okay. So that was one of the restrictions that I put, is that I said I consider only compositions and stuff. So this like one of the reasons why is because we have to build this kind of squares here if we want to do coherences. Now I also said like I'm only considering maximal variables. So what happens if I look at something that's not maximal? Well, let's try it out. So I'm going to consider this composition. And if you remember, this is the functoriality of the composition, like the usual composition of, on arrows and so on. But I'm not going to write it this way now because I want to consider another functoriality, and I don't want to mix up the minus and the plus and have different sets of minus and pluses. So I'm just renaming everything, but it's the same. And now I'm going to choose this variable g here. And I'm going to just try to apply the same recipe again. And if I do that, I notice that here I have the minus version and the plus version. And again, they are not parallel. And it's the exact same phenomenon. If I look at what's here, I have something, I go from minus to plus here, minus to plus here, and it's the same term from minus to plus, and I know how to go from minus to plus. It's the functoriality that I introduced just before. And so by using this kind of functoriality here, I could do this entire term here, functoriality with respect to g, and I get a thing here, and same a thing here on the other side. I get those two legs here, and now I can ask for this to be a filler for this square. And again, it kind of looks like an equation that you'd expect in higher categories, or at least if you look at that in the perspective of a two category, this is the uninterchange rule. There are plenty of them, but it's not just an equation. Now I have a cell that fills in inside, but I could also, again, I could also have chosen the opposite direction, and actually those cells are invertible. Right. So now what we've proved is that in some way, for any term that you can build in the theory of weak omega categories, if you take an upwards closed set of variables, and all of those variables are of depth at most 1, and I'll explain those conditions in a second, then you have this kind of square-shaped thing that you kind of want to fill, and yeah, you can construct a filler for that. So what it means to be upwards closed is that if x is a variable that appears in x, then, okay, thank you. Then all the variables that have x as their source or target also appear in it. And depth 1 means that all the variables that are contained in X are of dimension at least 1 less than the dimension of the term that I started from. So of codimension at most 1 in the term, if that makes sense. And that ensures that everything kind of stays neatly square shaped. And we're trying, like, we're working to lift that condition to have higher dimensional things, but then you enter the world of cylinders and it becomes a lot more complicated. Okay, so let me give you a maybe more surprising or more unusual example. If I consider, well, T, the composition again, but now instead of choosing X to be just F, I'll choose X to be everyone. It's kind of unclear what it means if I ask you, like, what is the naturality of the composition with respect to all of those variables? Like, you probably wouldn't know what it means. But if you follow the kind of algorithm and follow the pattern, it really is something that takes a bunch of data like this. And now notice that I'm selecting F, so I'm increasing its dimension, but since its source and target are also selected, instead of making it as a kind of bubble, I make it kind of a square, because I'm also like drawing lines that correspond to those B and C and A's. And out of this data, so what this tells me is that out of this data, which is this data here to which I apply some kind of transformation, I can get a filler for this entire square here, which is the composite thing. And so I'm able to build like a square composition. So that's not very surprising that in this weak omega categories kind of setting, you could build a square composition. But what's really interesting for us is that we've built that for every possible composition. There's a squared version of that if you follow the restriction that we have. And we kind of have a formal way of saying that we can see these as a naturality of the composition with respect to all of those variables, which is kind of unusual. So let me go very quickly over like maybe the one application or the one like fun thing that we've done with that. So if I start again with the thing I just constructed, but I rename everything because again I want to construct everything. And now, just for fun, I'll select all of those variables that I've put in red here, and I see what this gives me. Well, the entire situation that gives me is something that looks like two cylinders that are glued along each other like this, because you can see it as like increasing this, like doubling this alpha and beta, but also doubling the F and G as like, and making like a square, but inside of this triangle, so in this section, so that becomes the cylinder. And what we've shown is basically that in this situation, well, you can construct a filler for the entire outer triangle by composing the top thing, the bottom thing, the front thing, the back things, with the things that we've done recursively. And yeah, so in weak omega categories, you can, like, a generalization that we've done is that you can construct a composition for all the cylinders of any dimension glued along any face that you want. And this is something that you can obtain out of this like kind of mechanism. And yeah, very quickly, this is all implemented in a proof assistant, and you can also export it inside of homotopy type theory, which is kind of cool. And yeah, I think I'll stop there. Thank you.
I have a question, although I'm not sure I understood super well. You started off by telling us what functoriality might mean in your weak omega setting.
Yeah.
And then this work was about what naturality could mean.
Yeah.
So when you have infinitely many dimensions, it doesn't stop there, right? You'll have computations after that, and then some sort of coherence for all the n transport. Does your work address this, or if not, is it clear how you might extend this?
So
where does it even stop?
You see here this condition here.
Yeah.
And I'm saying depth 1, and just below I said that
square shape. Huh?
That makes everything square shaped.
But then
that is the thing that restricts you to something that looks like naturality. If you go to higher depth, which is like this thing that I haven't defined, but you know, if you go to higher, then you get like some more cylindrically shaped things, and those will correspond to higher dimensional transfers.
Your picture on the last slide, it seemed like you had modifications.
Well, yes, kind of. We have composition for this situation, but we don't have any way to state that this thing is associative in the correct way that you would state that this is associative. Like, it's not even like well typed to say this is associative. You know, you have to pad everything so that it works. But even like, okay, even this one actually, even this one, if you were to try to say this is associative, what you would do is like have a cylinder like this, where on the front you have 3 squares, on the back you have 3 squares, but they are associated differently. And then the top and the bottom are themselves associators. So it's kind of like, it's tricky to build. It's not something that's immediate. And we don't I actually don't know how to get that from just the depth 1 case. I think this comes from higher depth.
Is it clear how to generalize your methods to higher depth?
We're trying really hard to do that, so I wouldn't say it's clear because I'm struggling with it, but I hope that I will manage it one day.
Finishing a bit late, so if you have other questions, you can always ask them later. Let's thank the speaker again.
Thank you for that, and thank you everyone. You can bring back the black marks where coffee was served, so that location can take a back. And another thing for those of you who signed up to go for dinner, we'll go at 6:30 to Saga Indian restaurant, about 7-minute walk. In the meantime, it's sunny, so there's a park nearby, there's a pub, Marlborough Arms, about 3-minute walk from here. Otherwise, see you there at 6:30. It's on the website if you want to check out the site's location.
Can we go if we didn't sign up? Can we go still if we didn't sign up for dinner?
There's one, yeah, someone is not going, so you can take that spot, or you can fight.
Yeah, cool. Screw you guys.
Maybe also next to the spot won't change much. But the mug, remember the mug, please.
It's not like you've reserved a bunch of tables, is it? Or have you reserved a bunch of tables?
Well, yeah, I called them and I said there's gonna be like 25 of us, but let me.
This goes in the bottom. What? Yes.